Okay. Okay, great. So last week we covered accelerating genomics with a full lecture. So hopefully that was interesting. That's an exciting area, and I think that's very much related to what we're going to cover today. Because if you really want to make second level decisions in genomics using genomic analysis, you really need low latency memory. You don't have any other choice, in my opinion, because things are just too slow to go to even DRAM with existing latencies. If you want to do a lot of analyses, of course, on a lot of data, clearly. I think that's true for artificial intelligence applications, machine learning applications also. Increasingly, we will need low latency memory. And you know that people are trying to move computation closer to data to be able to do that. Or like Cerebras is doing, they're implementing machine learning accelerators on wafer scale engines where they have access to more than 18 gigabytes of memory. That's essentially low latency access to large amounts of data. And there's a reason why they're doing that. That's why this topic is a lot more important today. I was teaching this topic for actually more than, I don't know, let's say 8 years or so. And the importance of this topic is increasing. Again, this is very interesting. It's so fundamental, right? You want to have low latency because applications eventually demand it, even if they don't demand it today. And at that time, some people were saying, why do you want low latency? Applications don't demand it. And that's wrong, basically. I will say that there are a lot of applications that would make use of low latency memory if you provide it to them. So again, this is a place where you need to also stretch your minds a little bit and ask the question, if when people are saying we don't need lower latencies, is that really correct? Like what is their motivation in saying that? Are they ignorant, or they have something to gain about this? And I've seen both cases, basically. When people say, oh, we don't want low latency, they're either ignorant or they have something to gain from not having low latency memory. Okay, but clearly you can do a lot more when you have low latency, and I'm going to motivate this a little bit more also. So I think this is another area where naysayers have been proven wrong at this point. But these are the 4 key directions we've been examining. We talked a lot about security, reliability a little bit. I mean, we did consider safety implications, but we looked at memory aspects of security, reliability, and safety. We looked at data-centric architectures, computation memory 2 weeks ago, and we looked at genomics last week and earlier also in the course. But there's also more, of course, over here, AI, ML. Somehow the slide's a bit older, as you can see. Now we're going to talk about low latency. So we're going to cover all of these here, at least with some examples. There's, of course, a lot more to do. But I think when I think of speed and latency, it's really about solving the hardest problems. You may not need low latency for a random problem. Whenever you're writing into Word, for example, maybe you don't need low latency, sure. Maybe whenever you're presenting in PowerPoint, maybe you don't need extremely low latency. Although that's changing with virtual reality type of presentations, right? You need to consider everything in context. But when you go into the hardest problems, like climate modeling, trying to figure out what's going on with the world, then you need to actually deal with a lot of data and a lot of simulations and a lot of difficult tasks. And if you give up on latency, then you're going to be basically late, or you're not going to be able to solve the problem in time, basically. Usually, like when you're doing weather prediction, for example, you want to predict the weather for the next hour. You don't have a lot of time to do that prediction, and you need to consider a lot of data. Whenever you want to predict the weather in this particular square meter, as opposed to 10,000 square meters, again, you need to deal with a lot more data. And as a result, latency becomes a big bottleneck. Other hard problems, there are clearly many, many hard problems in the world, but I like these examples because they're visual. This is another example. As you can see, congestion is a big problem. And how to solve these problems is bigger, especially with self-driving cars, right? How do you avoid these things when you're doing self-driving, or when you're not doing self-driving? If you can predict these things very quickly and adapt to them very quickly, you can potentially fix these issues. So latency, again, is important here. And we've talked about genomics. Clearly, latency is important over there, right? If you want to get quick decisions. And I think modeling the brain is another example where latency is really important. And I think there's another picture that's here, not just modeling the brain, but also using brain-machine interfaces to drive, let's say, decisions that you make, for example, or to communicate with you in terms of some language that you don't understand, for example. These are really extremely latency-critical problems. Like if your brain is acting as a translator, online translator, when you're speaking with someone in Chinese, let's say, I don't know Chinese, so I can use that safely. Then your brain, the machine in your brain has to be really fast to be able to do that translation and communication, right? Clearly, latency is a problem. And I've already given you this joke related to Maslow's hierarchy. Maslow suggested that your physiological and safety security needs come first. And we deconstructed it. Well, in the beginning, we said that security and reliability are most important. But then we said, if you don't have energy, maybe you don't care about security and reliability. And maybe if you don't have speed, you don't care about any of that because you're not going to finish your task anyway. Who cares about your not being secure or not having energy, right? So in the end, maybe speed is very important. So clearly when I introduced this, I said in different conditions, you may need different trade-offs, and that's true, obviously, but speed is a really important thing that you cannot give up. Okay, so a big challenge and opportunity for the future is really designing fundamentally low latency computing architectures. And this is becoming increasingly important, as I said, with these increasingly demanding workloads and the need for more real-time analysis. Real-time in the sense that maybe it doesn't need to be hard real-time. So hard real-time is something where you miss the deadline, you have a drastic bad consequence. For example, the braking system of a self-driving car. You miss the deadline for pressing the brake at the right time, you may kill someone, right? Or you may hit something and you may be injured badly, right? So that's a hard real-time system. In that sense, you have to meet the deadline. There's also soft real-time where you may miss a deadline once in a while. It's not drastic, but if you miss too many deadlines, then the world becomes not so livable, basically. This is my cell phone, for example. If my cell phone is not responsive once a day, okay, I can tolerate it. If it's not responsive every time, if it responds 2 seconds or 5 seconds after I pick it up, every time I pick it up, then there's a problem, right? This is soft real time, clearly. I don't die in the end, but this makes me not use this thing also. Maybe not as often, or maybe only in critical functions I use it. So that's why I think it's good to distinguish between hard real time and soft real time systems, but they're both important in our lives today. And both of them rely on latency, basically. You have a deadline, you have to meet the deadline. To meet the deadline, you need to clearly, deadline is by definition a latency problem, right? If you don't do a task before X number of seconds, then that task is useless or worthless to you at that point in time. Okay, so that's why latency is important, especially in these real-time systems. And increasingly, systems are becoming more and more real-time systems, like a self-driving car, a drone that you're controlling, robots that are not running around, as you can see today, because clearly we have not succeeded in robotics as much as we think we have. But all of these things are bound by latency. And one of the reasons why we haven't succeeded, in my opinion, is latency and the lack of specialized architectures for robotics, for example. Okay, so if you don't believe me, I would recommend you take a look at this beautiful keynote talk at a recent conference. This is SysTor. This is a systems and storage conference that was in a couple of weeks ago, actually. I gave one of the keynote talks in this conference, and Satya, who was my colleague at CMU, gave another keynote. Satya is a pioneer in distributed systems. He's very well known for the Andrew file system, OpenAFS, and many other distributed systems contributions. And his keynote was beautiful in the sense that it was really forward-looking. It's good to have forward-looking keynotes in conferences, for sure. And it basically looked at edge computing, and this is the title, Edge Computing, a New Disruptive Force. And what he means by edge computing is things that are around here. This is tier 3 over here. And clearly, a lot of this is happening right now, but it's not happening as well as we want. And basically, whatever I said earlier jives very well with whatever he said in his keynote also. Basically, he said that we need a lot of problems to solve on the edge, and edge is really important for us. We cannot basically ship everything to the cloud because it's just too slow and too inefficient. So we need to do a lot of computing on the edge over here, as well as the cloudlets, which he has also pioneered. Okay, so I'm going to give you a couple of slides, and then I'll leave you with watching the keynote yourself if you're interested. But basically, these are the things that devices on the edge, like this, drones, sensors, smartphones, clearly, those are commonplace today. But these devices that are close to brain-machine interfaces, they're not yet, but I think the next step in these are brain-machine interfaces, and virtual reality or augmented reality clearly is another one. Clearly, you want to do analytics in the edge, in the sensors. You want to be highly responsive. So latency is clearly very important, both in terms of mean and the tail latency. So this is one of the examples that he gave clearly. So I'm going to motivate the lecture using this one also. But there are other things that are really important. You can see privacy, for example, is really important. Who controls the data and how do you actually ensure that your privacy is not compromised? Availability of the services is important because you may not have a cloud to back up if you're in the field doing edge computing. And also provenance is becoming increasingly important because different countries, for good or bad, again, have different kind of rules in terms of what data can be stored where, what computation can be done where. That's really partitioning the world. I'm not saying it's good or bad, maybe bad sometimes, I think. But basically, you may need to obey these. So clearly, you need to. There are a lot of interesting research issues here, and one of the ways he motivated latency, which is how I like motivating also, is if you actually are interacting with the humans. If you have a computer that's interacting with the humans and it needs to make decisions such that humans do not recognize the delays in the decisions. Basically, let's say replacing a human's brain, you really need to be fast. So you can see some of the numbers that he pointed out, and the references are in his talk where he gets these from. You can see that humans can tolerate latencies below 700 milliseconds for face detection. Face recognition is a little bit lower. Is this sound from a human? They can do it within 4 milliseconds. But if you really want to not destroy the experience of a human with VR head tracking, for example, virtual reality head tracking, then you need to have latencies less than 16 milliseconds. So you can see that the bounds are going lower and lower as you go from top to the bottom. So basically, the machines need to be better than humans because they also have a lot of overheads in their processing. So as you can see, that latency is really important for emerging applications and future applications especially. Okay, and we've already talked about some emerging and future applications where latency is important. So you're not unfamiliar with these, but I wanted to give this other perspective from someone I respect, as you can see over here. Okay, and you see that we have discussed why this is also a problem. So you can see that a lot of what we discussed actually jives with what Satya also discussed. We wanted this embedded device, which you can consider as an edge device that can perform comprehensive genome analysis in a real time. And there are many problems. As I mentioned, there's a huge privacy problem over there also, and security problem, and performance and latency problem. So there's a huge memory bottleneck. And memory bottleneck comes from part of the memory bottleneck is really the latency bottleneck. Okay, so before I move on to how do we make systems or understanding the latency issues first, I will also mention that we are talking about data-centric architectures, right? That's one thing we have been talking about in the past few lectures, especially with in-memory computation. But in-memory computation or processing data where it resides is just one property of a data-centric architecture. It's an important property because if you want to be data-centric, you don't want to move data, clearly, as we said. But having low latency and low energy access to data is a very important property because this, if you're data-centric, you really want to have quick access to data, low energy access to data. You need to store it low cost and need to manage it intelligently, as we also discussed earlier. So this lecture is really about, in the end, building a data-centric architecture by respecting how fast we can access data. I'm not going to talk as much about low energy, but you can see that in many times, reducing the latency also reduces the energy. Why? Because you're not going to exercise a energy-hungry interconnects for a long time. You're not going to drive things at high voltage for a long time. As a result, you will reduce both static latency and dynamic latency over time. Static energy and dynamic energy over time. Okay, we can discuss more about that if we have time later on. I'll point to some papers related to low energy. Okay, so let's start with fundamental trade-offs in memory latency. And you've already seen the slide. I'm going to just animate it very quickly. Basically, during the course of the history of main memory, latency has always been not as big of a, let's say, I don't want to call it a concern, but priority. Why? Because it was harder. Let me put it that way. There are two reasons. One, it's harder and it's more costly. Exactly because of these two reasons, people did not improve it as much. So capacity is a lot easier, as we discussed, right? Improving capacity is a lot easier because as you scale down the technology node size, your capacity improves. Yes, we're having reliability problems. Yes, we're having security problems. Yes, we're having all kinds of noise issues now because we're reducing capacity a lot into very small nodes today, but still it's not as difficult to improve, let me put it that way, because technology node like Moore's law or an equivalent of Moore's law helps you there. Yes, you need to solve the reliability and security problems that come with it, sure. Bandwidth is, again, not as hard to improve, but it comes at a cost. But it's not as hard as latency in the end. And we're going to see bandwidth a little bit also in a little bit. There was actually one question about pin count in Piazza. I didn't answer that, but I think it's going to be clear by the end of today's lecture that pin count is one of the most costly things. And if you want to increase bandwidth, you would like to reduce the increase the pin count of a DRAM chip so that you can transfer more bits in a given time. But increasing the pin count comes at a cost, as we will see, because these are costly. Pins are essentially very costly things to incorporate in the chip and on the periphery of the chip. Okay, and latency is harder because you may increase the pin count, yes, by adding more cost, or you may increase the frequency of the bus by adding more cost. But latency is a bit harder than that, actually, as we will see in this. Although there may be some simple things. If you think differently, if you change the mindset, saying that, okay, we're not going to consider latency as fundamentally hard, we're going to basically solve the problem, then you may actually find out really interesting ideas, as we will discuss. Okay, so the problem is memory latency remains almost constant. And clearly, this is at odds with what we've discussed earlier. Applications demand low latency. Right? So this is another area where there's a huge disconnect, I think, between the software and the hardware. The DRAM designers have a very horse-like mindset, let me put it that way. We've discussed it earlier. You have a mindset that's horse. You don't basically consider what's going on in the rest of the world. You basically want to maximize your profit and minimize your cost. And if that's your mindset, then what's being done also, of course, makes sense, right? Then your capacity needs to be the king, and you don't care about latency. That's why we're in the situation right now. Okay. So a closer look, actually, this is from a paper that I'm going to briefly discuss later on that we've written 4 years ago. But you can see that some of the latencies are increasing, some of the latencies are decreasing over time. There are reasons for it that I'm not going to go into right now. But the circuits change a little bit, and then these latencies increase or decrease. But clearly, latency is not decreasing significantly over the course of decades and decades. Okay, but we know that memory latency is critical for performance. I've given you many examples of this. I'm going to talk to you about one thing that's a bit worrisome, because some of the new DRAM types actually increase latency. So this is from a paper that we did a couple of years ago. We wanted to understand the complex interactions between a workload and application and different types of DRAM. And we wanted to do this experimental study. So let me tell you a little bit more about that. And basically, one of the key conclusions of the study is because newer DRAM types do not reduce latency, applications are losing performance when you move to some new DRAM type from an old DRAM type, which is not nice, right? Ideally, as technology improves, with a new DRAM type, you should get better performance. But if that's not happening, that's not good. Okay, but let me also give you the landscape of main memory a little bit more when we talk about this work. Today, manufacturers are developing many new types of DRAM. One of the reasons is the scaling issues, technology scaling issues, because they're also figuring out that when you have one-size-fits-all DRAM, it doesn't cater for all of the applications. So that's good. That's progress, I think, on the memory side. That has happened in recent years, mostly. Clearly, DRAM limits performance and energy improvements, and new DRAM types may overcome some of those limitations. We will see some of them. Like 3D stacked memory clearly overcome some of the bandwidth limitations, right? Memory systems now serve a very diverse set of applications, and because of that, it's good to proliferate or have heterogeneity in the different types of memory you have in the market. And that helps because now people can choose which DRAM type they want to use, right? Of course, the question is it easy? Which DRAM type works best with which application? This is a question that's faced by many system designers. Whenever you're designing a system, it doesn't matter what kind of system it is. As long as you want to connect DRAM to it, you should always ask the question, what type of DRAM? Because today there are many different types of DRAM. Of course, how do you do that study? Well, I think simulation is really important. And we didn't have a lecture on simulation, but we will at some point have it. So simulation lets you explore which DRAM types can work best with which of your applications, or even if you have one application that you care about with that application. But it's difficult to intuitively understand which one would work due to the complexity of the interaction, because different memory types have different trade-offs. And this cannot be tested methodically on real systems also, because if you look at a real system, a single CPU has one type of DRAM interface. For example, my cell phone has an LPDDR DRAM interface. Actually, I'm not sure because this is really old. It could be even DDR. I believe it's LP, but fine. My computer has a DDR3 interface. It's one type of DRAM. Some GPUs have high bandwidth memory interface today, but they don't have an interface to some other type of DRAM today. So you cannot basically take a real system, execute your application, and compare the results on 10 different types of DRAM. Why? Because your system doesn't support it. Right? Clearly, this is obvious, hopefully, if you know how systems are designed. But now I told you how systems are designed. You cannot do this study on a real system. And one of the reasons why systems do not support multiple different types of DRAM is because it's extremely costly. Again, think about pins. We talk about pin count on Piazza a little bit, right? If you want to have one DRAM interface, it's 64 bits today, let's say. 64 bits is low, fine, but that's what it is today. So you need to have 64 bits for one DRAM interface, let's say DDR3. And then you want to have another 64 bits for, let's say, GDDR5. That's a graphic type of DDR. Now you have increased your pin count. Well, you've doubled your pin count dedicated for memory. That's extremely costly. Why? Because pin count is essentially what you need to, essentially you need to have physical pins on the processor die to be able to do this. Those physical pins are costly. But also internally in the processor, this is heavy analog circuitry. So you need to have I/O, what is called I/O pads, input-output pads, that are heavily analog. And you need to be able to run them at very high frequency. So today's DRAM frequencies are really extremely high, actually. Those are some of the highest speed analog interfaces that we have in systems today. So the cost comes from the additional circuitry that you need to add to the chip, which is a lot large, and also the additional pin that you need to have physically on the chip. And clearly, the number of pins you can have on a chip is limited by your chip area. In the end, you can do the calculation, right? If your chip periphery is some number of millimeters, if you count all of the periphery, and if a pin costs, let's say, n millimeters, you need to divide the periphery area by n. But not just that, because there needs to be some distance between the pins that should be empty, because you don't want crosstalk and analog interference between these very high bandwidth communication lines, high frequency communication lines. As a result, there's only some number of pins you can afford to have on a chip. And today, actually, we're pushing that boundary. You cannot afford to add more pins. If you want to add more pins, you may need to actually increase the size of your die. That increases your cost, clearly, right? Because as you increase the size of your die, it becomes more costly because you can produce fewer dies in a given wafer. So now you understand, hopefully, why pin count is so important. And you don't really like to minimize it, but you don't want to, you don't have the freedom to increase it arbitrarily without running into huge cost issues. And I haven't even talked about the power issues, right? Because you need to power these pins. And clearly, high bandwidth interconnects that are operating at very high frequency is not easy to power. So your power consumption also goes up. It's not just your area, but also your power budget that needs to go up. As a result, you get basically double charged in terms of how much cost you need to incur in your systems, right? So that's why pin count is very constraining in existing systems. And this is two-dimensional, of course. In two-dimensional systems, pin count is a problem. But once you go three-dimensional, it becomes better, right? As we discussed, if your memory is three-dimensional, if you have a logic layer, and then if you put memory layers on top of that, you could connect the logic layer and the memory layers not with pins, because you're not going off chip anymore. You're doing some sort of bonding at the top. First of all, you have more surface area, clearly. But also, you can actually use what is called through silicon vias today. That are not pins. They're not exactly small vias, but they're somewhere in between, essentially. So you can have many more of them at lower cost, let's say. So three-dimensional integration, that's why that's one of the reasons why three-dimensional integration is very, very promising, is it basically overcomes this pin count bottleneck that exists in two-dimensional systems. So keep that in mind always. That's one of the big benefits of three-dimensional integration going into the future. And if you can actually have even more aggressive three-dimensional integration systems, now you can have only vias in between layers, and now you can have maybe millions of them, right? So as opposed to, let's say, around 1,000 pins today. So today in a system you have 1,000 pins, but only 64 of them are dedicated to DRAM. There are many, many other pins that are dedicated for other things, actually. Maybe we'll talk about them later on. But for example, for powering the system, you need to have some pins. For control of your processor, for debugging of your processor, for many, many things, you need to have different types of pins. So DRAM is only part of it, basically. Okay, so I digressed a little bit, but I think it was important to discuss it over here. Basically, one of the reasons why you cannot have many different types of DRAM attached to a single CPU today is because you cannot afford to have that many pins. But it's not only that, you cannot afford to have that many analog interfaces as well. And those analog interfaces actually enable you to communicate with the pins, but those are extremely expensive. So it actually takes a lot of time to build a high-speed analog interface, assuming that you have the pins and I/O pads already ready. The analog interface that you need to have for GDDR5 is expensive. That's true for DDR3, DDR4, DDR5, all of them also. Okay. Let me see. So as far as I know, today's DDR standard work with differential signaling, which actually uses double the amount of pins that would actually be required. That's true. Is there a good reason for that other than that the frequency can be pushed more than X2 higher? Yeah, exactly. Basically, the goal is bandwidth. The reason people do that is to gain higher bandwidth, and that's the best way they can gain higher bandwidth today, unfortunately. And they made the trade-off to actually do that today. Yeah, so you can see the importance of the bandwidth over here. Okay, but we're not going to go into the details of the lower level implementation of the DDR interface. And if you're really interested in this stuff, maybe you should really take a look at how these things are implemented. And there's some open source DDR interface that you can work with. One is called Light DRAM, for example. If you're interested, let me know clearly. Okay, so let's take a look at the study. Basically, in this study, we look at it's an experimental study. It's an empirical simulation-based study. And we look at the combined behavior of workloads and DRAM types. And we examine more than 100 applications and 9 different DRAM types. And we want to understand which DRAM type works better with which class of application and why. So it's a very empirical experimental study. And I think these studies are really important to do so that you can gain insight into the system. Before we did the study, I don't think we had this insight that we had. But you can see some memories that are out there today. So these are standards. You don't need to know exact differences, but this paper summarizes some of the differences. And this is one of the more potential readings if you're interested in reading it. So you can see that going from DDR3 to DDR4, banks have increased, but they've introduced something called bank groups, which means that you cannot access all banks in parallel. You can access bank groups in parallel, even though you have more banks. So GDDR5, you can see over here. So this is the idea of bank groups that I'm not going to talk about a lot. But going from DDR3 to DDR4 increase the latency and increase the latency over here. In going from DDR3 to DDR5, this is graphics memory, increase the area and power. So this increased the bandwidth a lot, actually, the GDDR5 by increasing the signaling, as we just discussed, signaling rate, let me put it that way. And that increased the area and power significantly. So these are 3D stacked memories or potentially 3D stacked memories. HBM is used at 2.5D stacked using interposers. But you can see that interposers could be limited by the pin count, as you can imagine. So you can see these make different trade-offs. For example, hybrid memory cube increase the banks per rank, but increases 3D stacking. So you can see 3D stacking over here pictorially. But there's one downside. Hybrid memory cube actually reduces the row buffer size. And as a result, it has higher latency also. Okay, there's one more question. Is increased latency and area power because of bank grouping? Yeah, bank grouping actually adds additional latency. Yes, whenever you need to switch between 2 bank groups, you actually incur additional latency. So that's one of the reasons. And power is also for that reason, yes. But there are other reasons also that I'm not talking about over here. One of the reasons why DDR4 increases power is also bandwidth increases in DDR4 compared to DDR3. Okay, so you can see that in HMC, you get narrower nodes and higher latency. And there are a bunch of other standards, like LPDDR is low power, as you can see over here, and wide IO 1 and 2 are more mobile type of standards. And you can read about them in the paper. I'm not going to talk about that. I'm not going to go into details of any of these, but clearly this shows that there are different types of DRAM that are there for different reasons. And we want to understand which one works better with which one. But I'm not going to even do that. I'm going to give you some of the key takeaways that we have. So this, for example, gives you an example. These are some common OS operating system routines, like file IO, process forking, some benchmarks that are actually designed for that purpose. So we look at those workloads, and we see basically that going from DDR3 to DDR4, speed up is negligible, right? You can see that 1.0, this is normalized to DDR3, 1.0 is DDR3's performance. DDR4 basically doesn't buy you any performance, right? And in the paper, we have some cases where DDR4 actually loses performance. But this begs the question, do you really want to go to a newer memory that's higher power if you're not gaining performance? And what is worse is some work on HMC, for example, hybrid memory cube, which is a 3D stacked memory, loses performance on some workloads, about 10%, more than 10% over here. So this doesn't sound good. So GDDR5 is really good, actually. You can see that it improves performance on many workloads. Because, why? Because it reduces latency. It also increases bandwidth at the same time. So this is really expensive memory that's used in GPUs. HBM is not as good, as you can see, because there are some other trade-offs that they make that loses performance. But GDDR5 is really good for these workloads. So you can see how not necessarily intuitive these interactions are. You need to really understand, simulate, and figure out what these interactions are. But the one big takeaway over here is the DRAM types that increase latency in order to provide more banks or higher throughput essentially do not make a good trade-off for applications that are latency bound. And these are the applications that you see. A variety of desktop, scientific, and GPGP applications are also similar here. Okay, so essentially the takeaway is these DRAM types may increase your parallelism, but if the application cannot be rewritten or doesn't take advantage of the parallelism, meaning bandwidth plus the bank level parallelism that you get, you're not going to get benefits out of this new type of memory that makes the trade-off of increasing latency for increased parallelism or throughput. Okay, so let me give you the key takeaways from the study. Basically, the first one is DRAM latency remains a critical bottleneck for many applications, so people should improve that. Bank parallelism, even though some memories increase it, they're not, the parallelism is not fully utilized by a very wide variety of the applications we examined. Spatial locality is still important if it's exploited by the memory subsystem. So if a memory type makes a trade-off of reducing spatial locality, meaning reducing the row buffer size, but increases bank level parallelism, that's not good actually. And we've seen this with hybrid memory cube. You can see these results are like that, basically. If hybrid memory cube loses significant performance, sometimes, not always. And for some classes of applications, low power memory is actually very good because it can provide energy savings without sacrificing significant performance. So this is also interesting. So it's good to look at, actually. I think based on these are actually good key takeaways that both architects as well as system designers, as well as software designers can take away if they're using a particular type of memory. And in the paper, we give some takeaways or implications for both the architects, memory architects, system designers, and software designers. And you can take a look at that. But I think low power memory is very promising. These low power memories, LPDDR, for example, use a different type of signaling to reduce the power of the signal. Usually they reduce the bandwidth also. So that's the trade-off. And sometimes they increase the latency. But in some applications, you can. This is a good trade-off, and it's good to understand how you can be low power and low latency at the same time. Okay, so basically that's the conclusion from the study. I'm not going to talk more about this, but there are more key observations in this work you can take a look at. And the tool where you can model a lot of these memories is also open source. It's a version of Ramulator, which I briefly mentioned in one of the earlier lectures. Okay, and you can read the paper clearly here. Okay, So good, people are asking questions. Please keep asking questions. I'll keep monitoring my screen over here. But let me continue over here so that we're still in the motivation part. But I think motivation is really important because clearly you can see that the world is having some motivational problems also sometimes on such an important issue like this. Okay, high memory latency is a significant limiter of system performance and energy efficiency, and it's becoming increasingly so with higher memory contention, multi-core and heterogeneous architectures. Remember that we talked about memory performance attacks, for example, or interference between multiple applications. And whenever you have this sort of contention, now you need more bandwidth. And that exacerbates the quality of service problem, and that affects the latency of the application. So whenever you have more contention, your latency is also increased. So latencies are becoming worse actually in existing systems. And as we discussed, memory latency, having long latencies is bad for the system in general, because people try to do a lot to tolerate those latencies, both in hardware and software. If we didn't have these latencies in the first place, perhaps the world would be a much better place, right? So basically, in the hardware side, processor designers do a lot to tolerate memory latency. And we've discussed some of these, right? And let me give you one slide from my own PhD proposal. This is a slide that I used in 2003 when I was doing my PhD proposal. I use it again in my PhD defense, and I still keep using it. As you can see, I didn't change anything. Even the logo is here. But these are conventional latency tolerance techniques that people have implemented in processors for decades and decades. And they have not changed. I mean, clearly there have been a lot of research in these, and we've discussed some of them briefly, and we may discuss some of them again later on. But these have been very conventional. And let's take a look at them. These are caching, prefetching, multi-threading, out-of-order execution. They all add complexity into the system. And clearly, they're very widely used, right? We all have caches, we all have prefetchers, we all have multi-threaded engines, simultaneous multi-threading or fine-grained multi-threading. GPUs have massive multi-threading, for example, but even CPUs have 2 or 4 threads today. Out-of-order execution, we all have out-of-order execution machines in our cell phones, for example. So clearly, these are very high impact, and they're used. But caching may not always work. Especially when you have random access, when you don't have good locality. Prefetching may not always work when you don't have regular memory access patterns. Multi-threading doesn't help your single thread latencies, because your single thread can be very important, right, to you. You don't care about 10 other threads, or you may not be able to partition your program to 10 other threads. As a result, multi-threading may not help you. Out-of-order execution is actually the one that can potentially help a single thread the most by tolerating the latency of memory accesses that cannot be prefetched or cached for whatever reason. But this may not always work also, because this is very inefficient. It requires extensive hardware. And if there are lots of dependencies in the program, this may not actually buy you a lot of performance. So clearly, these are conventional latency tolerance techniques. And I motivated my PhD proposal saying that out-of-order execution can be made efficient to tolerate memory latencies with what I'm going to propose. And I'm going to talk about that also, because I think that's very important. But keep in mind that these techniques are all there to tolerate latency. They're processor-centric. What do I mean by that? For example, caching reduces the latency of access of data that you're going to touch again, but from the processor's perspective, right? The first time the processor touches that data, it still needs to incur high latency. Prefetching also aims to reduce the latency of data from the processor's perspective, right? Not memory's perspective. The first access or the prefetch that goes to memory still incurs high latency. Multi-threading clearly doesn't even try to reduce the latency. This is a true latency tolerance technique. From the perspective of the thread that needs the request from memory, it's going to wait. But hopefully its work is going to be overlapped with other work that's going on in other threads. Out-of-order execution, similar. It tolerates latency. It doesn't reduce latency. The work that's the waiting time for a memory access is overlapped with waiting time of other accesses plus other computations. Okay, basically the takeaway is none of these really fundamentally reduce memory latency. You still need to go to memory and bring the data, and take a long time to do that. Let me tell you what I proposed after I presented the slide, basically. Our proposal is actually also conventional in the sense that it's processor-centric, but I think it's important for you to know because it's a more efficient way of parallelizing cache misses than what out-of-order execution can do. We call this run-ahead execution, aptly. So ideally, you would like perfect caches in a processor-centric paradigm, right? you compute, you access the data, you get the data back from the cache, you get a cache hit, no problem. In the next access to load 2, you basically have a cache hit. So you never need to stall due to a cache miss. That sounds good, right? Clearly, we don't have that kind of world. But it's good to always talk about the ideal. Ideally, this is also zero latency, right? Okay, but today with out-of-order execution machines, what happens is you compute, you get a cache miss. This cache miss needs to go to memory. And while it's going to memory, for some time, you can compute, you can continue computing because you can fetch some instructions, you can buffer them, etc. But at some point, your instruction window becomes full. In today's machines, for example, you may have a 256 entry instruction window or 128 entry instruction window. You can actually fetch, decode, and execute 128 instructions while waiting for a cache miss. Okay, which is not a lot because if cache miss is 500 cycles, and if you're fetching 4 instructions per cycle, 128 is not a lot, right? You will stall very quickly, as you can see in this picture. And once your instruction window becomes full, the processor stalls. It cannot bring in new instructions, so it cannot overlap the latency. And the stall continues until the load miss comes back from main memory. And at that time, the processor can continue computation, and it stalls until the next miss. It computes until the next miss happens. And soon after, the processor's instruction window becomes full, and then the processor stalls again. Now, this doesn't sound good, right? Clearly, we're stalling a lot in a memory-intensive program. Now, run-ahead execution's idea is very simple. You compute, you get a long latency cache miss. Now, the long latency cache miss becomes the oldest instruction in the machine. At that point, you say, oh, this cache miss is still pending. It's going to take longer and longer. Well, it's going to take hundreds of cycles. So you take a checkpoint of the architectural state, which is the registers and program counter. And at that point, you say that I'm going to keep executing, but I'm going to go into a speculative mode called run-ahead mode. In this mode, I'm going to not stall the instruction window. I'm going to keep fetching instructions as if nothing happened. But for instructions that are dependent on this cache miss, I'm going to mark them specially, and I'm going to throw them out because I don't have the data for this cache miss. But I know which instructions are dependent on it because I'm doing out-of-order execution. So those instructions, I'm going to throw them out of the machine. And all of the other instructions I'm going to execute, I'm going to throw them out of the machine once their results are ready. And I keep going basically in the program path. I keep executing the program speculatively because I've thrown out the instruction that made me stall otherwise. Now, while I'm executing, hopefully, I will reach this load 2, and load 2 is independent of load 1. So I can generate its address, and I can find out it's a cache miss. And at this point, what I have done is I've reached load 2 much earlier than I would in a conventional processor, and I can parallelize the cache miss of load 2 with cache miss of load 1. Okay, so at some point, load 1's cache miss comes back, and I say, okay, I want to exit run-ahead mode. So I flush the pipeline, I go back to the checkpoint, and I restart from executing load 1. Now load 1 is a hit because clearly it was serviced right before, and I can continue computation as usual, normal. I'm not in run-ahead mode anymore because load 1 that caused entry to run-ahead mode came back, and I restored the checkpointed architectural state back into the machine. It's like a small context switch, right? You can think of it that way. It's a very small context switch where you're switching to the same program here, but you're executing it speculatively. And then you're switching back to the same program from the point where you checkpointed the architectural state, right? Here, basically, you're switching in a speculative thread, if you will, that's doing speculative prefetching for you. Okay, I compute, and when I get to load 2, it actually hits in the machine in the caches because I already serviced its miss. Why? Because instead of stalling over here, I did something useful called run-ahead execution. I speculatively execute the program, prefetch the data into the caches. And as a result, I've saved a lot of cycles. It's not as good as perfect caches, clearly, but you need to do something else to become closer to perfect caches. At least it's closer to perfect caches than this existing system. So that's the idea, as you can see. I like this idea. It's beautiful. And we may actually cover it in more detail later on, but I wanted to give you the basic idea. And the hardware cost of this is relatively small. Certainly, you don't need to increase the instruction window size to become 2,000 entries. You can actually keep it at 128 entries and get the benefit of a large window this way without increasing the hardware complexity. Okay, And we've actually done a lot of studies in terms of the performance improvement. This improves performance significantly with little complexity, but I don't want to give you our results. These are results from industry that have replicated our studies. It's a processor called Sunrock, and this is one of the chief architects of the processor. He presented this in a conference where he showed, they call the scout threads as opposed to run-ahead, but it's essentially the same thing. Scout threading versus no scout. No scout is conventional processor. Scout is non-conventional run-ahead execution. You can see that if your cache size is 512 kilobytes, you get 40% performance, which is very much consistent with the results we had. And you can see they have done other studies. For example, if your cache size was 4 megabytes, if you implement with run-ahead execution, you get the benefit of the cache size of 16 megabytes without run-ahead execution. So basically, run-ahead execution buys you about 12 megabytes of space on your chip. And these are on commercial workloads that they have tested. Sunrock was designed to be a commercial processor that can execute transaction processing workloads, for example, in banks or web servers. Okay, so you can see that this idea clearly improves performance. And if you're interested, you can read our original paper as well as a shorter version of it that was selected as an award paper. Okay, and there are more readings that I'm not going to talk about right now. So you can ask, okay, this is not efficient. How do you make it efficient? Clearly, that's important. How do you do this prefetching efficiently, run-ahead execution efficiently? And how do you parallelize dependent cache misses, which is a very tough problem, is also discussed over here. Okay, there are other issues over here that you may want to look into if you're really interested in this idea. I really like this idea, clearly. I spent 5 years of my life working on it, my PhD thesis on it, and looking at all different aspects of it. And in the end, multiple different processors in industry actually implemented it. IBM Power 6 implemented it, and they actually have written papers about it. Sunrock implemented, and there may be other processors who implement it, but we don't know much about it. Actually, a version of this is this exists in GPUs also. GPUs can do some limited sort of under the hood run-ahead execution. Yeah, okay. But okay, this is good. These are all good, actually. I think all of these are good. Caching, prefetching, multi-threading, out-of-order execution, run-ahead execution. None of them really fundamentally reduce the memory latency. They basically are all there to tolerate the memory latency. So, but there are two, we would like to really fundamentally reduce the memory latency, basically. And there are two major sources of latency and efficiency in existing systems. One is modern design. DRAM design is not modern DRAM is not designed for low latency, as we've discussed. Main focus is capacity. And the second is modern DRAM latency is determined by worst case conditions and worst case devices. So basically, the latency is determined by worst case operational conditions, let's say 95 degrees Celsius, and worst case devices, any acceptable device. If a device is not really good, manufacturers still put it out because they actually add a lot of margin to the latencies today. This is a way of actually enabling your yield, your chip yield to be high. You specify your latencies to be very high. As a result, chips that are weak, meaning chips that operate closer to those high latencies, can still be acceptable. You can still market them. Right? So this is not great, I think, in my opinion. Basically, in the end, latencies are determined by the worst case. Even though for most devices and for most operating conditions, you don't really need that latency that's dictated. We're going to talk a lot about that. And this is, I think, the low-hanging fruit, meaning by shaving these latencies that are really not needed for devices that you're using and for conditions that you're using the device in is a really great way of reducing latency. Actually, I may talk about an anecdote about this later on when we talk about this, because a lot of gamers actually do this. And I received a lot of emails over times from gamers saying that they learned a lot from our papers that discuss how to reduce memory latency, because we actually looked at how to reduce memory latency based on devices and based on conditions. And these are the folks that really care about the latencies, because any slowness that happens that affects their game experience is not good for them. So they're willing to go into the BIOS and reduce the latencies. They're willing to test the latencies of their chips and configure, if possible, in their BIOS to reduce the latencies, they're willing to do that basically. And these folks are actually perhaps the cutting edge in this. Out of everything, gamers, right? Clearly, GPUs have been developed to be so well. One of the major reasons is gaming industry in the end, right? Because you really want to be as close to reality as possible. And these folks, gamers, I think rightly so, are quite picky in terms of their user experience that they get. So they will be at the cutting edge. So this is important. I think I've already given you a part of the story, if you will, but clearly there are people who care about it, and gamers whom we did not discuss before are actually a good chunk of it. Well, not a good chunk, let me put it that way, are the chunk who are willing to take all the risks to reduce the latencies. Let me put it that way. Okay, but these two things are really, both of them are true. And we're going to start with the first one over here. So our goal is really to reduce the memory latency at the source of the problem, basically by actually getting rid of these two sources of latency inefficiency. So we're going to talk about truly reducing memory latency. But before we do that, let's try to first understand what causes the long memory latency. So this is another way of describing what I described in the previous slide. The first reason is we have long memory latency because of the design of the DRAM microarchitecture. The second is because of the DRAM specification, let's say. So you can think of this is the DRAM microarchitecture. Microarchitecture is designed to maximize minimize cost per bit or maximize capacity per area, not minimize latency. As a result, your latencies increase because of the design of the microarchitecture. But the architecture, which is the interface that's exposed to the user in the DRAM, specifies the latencies to be long also. And this is because they specify one latency parameter or one set of latency parameters in a one-size-fits-all approach. That set of latency parameters does not change depending on temperature, does not change depending on DRAM chip, does not change depending on parts of a DRAM chip, does not change depending on supply voltage levels, and clearly does not change depending on what application is accessing it or what data is stored in it. So basically, it's very one-size-fits-all. You have one set of parameters, let's say 55 nanoseconds to do row cycling time in DRAM, and you use those set of parameters. That's it. It doesn't matter whether your temperature is 0 degrees Celsius or 100 degrees Celsius, you're using that set of parameters because DRAM manufacturers said so. And this is very bad, I think. This leads to a lot of margin in latency that we're not exploiting. Okay, so let's talk about the first one first, though, because I think this is also very important. And you've seen some works like Figaro, which was presented last Friday, that tries to reduce latency and also enable data movement inside DRAM. But before we go into it, let me briefly review what's inside a DRAM chip. So this is a DRAM module. You can see you can plug this in to your systems. Now, clearly, cell phones don't have this. Cell phones actually solder the DRAM chips inside. They don't have this DIMM module form factor, but many systems have this module form factor. And if you look at a single chip, it looks like this. And we're going to look inside the single chip in a little bit. You can see the banks actually in these single chip. You can see 8 banks over here. And you can actually, if you go to this Chipworks site, or if you go to Anantech or some other website, some people have actually reverse engineered what these things look like. And you can actually pay money to some of these companies to actually do it for you if you're really interested. But clearly in the design of a DRAM chip, there are many goals, and cost is the dominant one. Latency is not a dominant one, as we discussed. Bandwidth, parallelism. Bandwidth and parallelism are different. Bandwidth is throughput in terms of transactions per second. Parallelism is overlapping of different requests inside different banks, for example. And both are important, clearly. Parallelism enables lower latency potentially, or hiding of latency. Bandwidth clearly enables faster transfers or more frequent transfers. Power, energy, reliability, security, and a lot of other things that we've discussed. I'm not going to talk about that. Clearly, it's a complex problem to design these chips. It's always a trade-off between these, as we've already also discussed. Right? We're going to examine the latency and cost trade-off a lot in these lectures. Okay, so DRAM chip looks like this, and this is what we're going to construct in a little bit. So a DRAM chip consists of a bunch of subarrays. This is just pictorial. Internally, it has many subarrays, actually. I just wanted to show this to be visible. So this is one subarray, this is another subarray, another subarray, another subarray. So these are 4 subarrays, or you can consider them as 2 subarrays. It's not that important as long as you know the operation. So let's build this up. We're going to go back to this chip, but let's build this up from a single sense amplifier and a single cell. You know how a sense amplifier works by now because we talked about row clone. It's a double inverter, cross-coupled inverter. And we know this very well from the digital design of digital circuits and computer architecture clearly. There's an enable signal for this, and there are two stable states for the sense amplifier. One is this side is VDD, and the other is this side is 0. So this is a logical 1, and this is a logical 0, as you can see. And we know all of this, so I'm going to go through this relatively quickly to build up. And when the sense amplifier is not enabled, this state is maintained. But once the sense amplifier becomes enabled, the sense amplifier amplifies the difference between VT and VB over here, and it pushes this to VDD and pulls this to 0. Okay, and DRAM cell is another fundamental component. So you can see the empty state, which is logical 0, fully charged state, logical 1. And the DRAM cells are small. As a result, they cannot drive circuits, and reading destroys their state. So how do you connect a capacitor to a sense amplifier? Well, you need to have something called a bit line, basically. And this is the bit line over here. So we connect a capacitor to the sense amplifier using a bit line. And whenever, and an access transistor, okay, you never forget the access transistor, and you need to have an access transistor to ensure you can control the connection between the cell and the bit line. And whenever you enable the access transistor, so assume it's a charged cell, whenever you enable the access transistor, the charged cell loses some of its charge. It perturbs the bit line, and bit line is in the reference voltage, as you can see, it's 1.5 VDD. And bit line is perturbed a little bit because the cell stored little charge, and this perturbation causes the sense amplifier to kick in, and it becomes enabled. There's some timed circuitry that enables this internally, and once it's enabled, the sense amplifier clearly amplifies the charge because this is slightly higher than this one. The top of the sense amplifier has slightly higher voltage than the bottom of the sense amplifier, and as a result, it drives the data back, or the charge back, into the cell. So this is the reading of a cell as we know. Now, how do you build a subarray? Essentially, this is a bit line and this is a single cell. We string together many of these cells in the bit line. Okay, that sounds good, right? And these are the rows now. So this is your subarray, basically. Or you can consider it as two subarrays also. You can consider one subarray depending on how independently you can control it. So this could be a single subarray, or this could be two subarrays. Fine. But I think of these as two different subarrays, actually. Subarray 0 over here and subarray 1 over here, because this one really operates on the other side of the sense amplifier. Okay, so basically these are two subarrays sharing the sense amplifiers. We're going to talk more about subarrays later on, but keep this in mind. Okay, now how can you scale this up? Basically, these have two different row decoders. This could be addresses 0, for example, addresses 1 over here. You can pick one bit going from here to there, distinguishing between the two subarrays over here. But if you want to scale this up, you can add more of these, and now you're getting closer to banks, right? So this is one bank that contains 4 subarrays in this case, right? In existing systems, it contains 64 to 128 or so subarrays. And as we discussed earlier, to get data out from this 8 kilobits, we actually use long global bit lines, long and big global bit lines. And they cannot be a lot. They cannot be 8 kilo bits. So you can only have 64 bits of them, for example. And this is an example. And then you drive those 64 bits out of the DRAM chip. And you need to have addresses, of course, both to the rows and the columns to get them out. Okay, in the end, your chip looks like this, basically. And your memory channel is very small, 8 bits. Your bank I/O can be even larger than that. Why? Because this is a very precious resource. As I said, the DRAM market is very much cost-driven. Increasing the size of your pins, or increasing the size of your chip by adding more pins, increase your cost. And DRAM market has very low margins in terms of each chip. So people are very reluctant to increase the size of your memory data out pins or data in pins, actually. And 8 bits is very commonly used. There could be 16, there could be 32. I believe there are also 64, but they're more expensive chips, basically. Basically, if you want to get chips that have larger pin count, you need to pay more because it costs DRAM manufacturers more. Okay, there's one question over here. In a paper I read about local and global row buffers, where would they fit in here? That's a great question. Basically, let me go back to this slide. So this array of sense amplifiers, that's also called a local row buffer. And this bank I/O, it's really a global row buffer. So hopefully that makes it clear. We're going to see this again, but local row buffer is always the sense amplifiers Maybe they should have been called local sense amplifiers, let's put it that way. And this is really bank IO or global row buffer, even though it's not a row, as you can see, right? It's 64 bits. So some, unfortunately, these are not always clear in all of the papers, but this is really the clarity over here. Okay. Okay, so there's a shared internal bus between the banks. It's 64 bits, but the memory channel is 8 bits. So what happens is you get 64 bits and you buffer it in the global row buffer, as your colleague mentioned, or bank IO, and you put it out 8-bit by 8-bit because your channel, memory channel, the pins is much smaller than the size of your global row buffer, as we've discussed. Okay. So this is also called the burst mode, meaning you actually bring 64 bits and you burst them out in 8 DRAM clock cycles because your channel is much thinner, narrower compared to your bank IO bit. Okay, and the main reason is cost again. Okay, so DRAM operation. If you want to get this piece of data from this row, you first need to activate that row. Send an activate command, and this brings the data into the local row buffer here, which is the sense amplifiers. And now the sense amplifiers have the data strong, okay? It takes some time, clearly, some delay. And then once the data is here, there's a timing constraint that you need to obey. And after you obey the timing constraint, you assume that the data is stable over here. That's the handshake between the memory controller and DRAM. And you can now issue read and write commands to this DRAM subarray that you activated. Or DRAM, there's no distinction in today's DRAM between subarrays. So the DRAM bank you've activated. So whenever you issue an activate, the local row buffers get activated. So you get all of the row over there. And then what you need to do is you need to issue a read and write command from the memory controller. So if you do a load store, all of these get translated to commands, command sequences that I show over here. Okay, the memory controller issues a read and write command, which essentially is sent to the DRAM with a column address and to the subarray that you've activated clearly, and using the global bit lines that are not shown here clearly, the data comes out to the bank IO, and then it goes out of the chip through the read and write command. Okay, one column. And then if you want to activate some other row, you need to issue the precharge command, and the precharge command goes to the entire bank. It essentially precharges all of the bit lines into VDD over 2. Once the bit lines are precharged to VDD over 2, clearly the row buffer doesn't contain anything anymore, because row buffer or local row buffer or local sense amplifiers contain something only if they've amplified the data, right? It cannot be VDD over 2 on both ends, right? That means it's not active at that point. Okay, there's one question. Let me take that quickly. Is a 64-bit integer, for example, stored across 8 banks for better parallel access? So normally, no. Normally, a 64-bit integer is stored within a single bank, but it doesn't have to be. Of course, it depends on your layout. But I think the most efficient is really storing it. Well, that's a good question, actually. Is it? Do you store it across 8 banks? As far as I know, people don't do that today. You could do it by changing your mapping mechanisms, but normally I believe what is done with a 64 bits is you get well, actually normally that what I'm going to describe is done. You get 64 bits into the bank IO, and then you take it out 8-bit by 8-bit. Now this what happens is actually we have not gone into the DIM. I'm not sure if we will go into the DIM. Okay, we don't have the DIM over here, so let me go back to the DIM. What happens normally is you get a full cache block. You don't get a single 64-bit. So how do you get the cache block? So you have one bank here. So one bank here, one bank here, one bank here, the same bank. That's across 8 chips. So this is a rank, actually, or a module. In a rank, you have the same bank across all of these different chips. And if you want to get a 64-byte cache block, you get 64 bits from each of them. Does that make sense? So consecutive 64 bits are in consecutive chips normally. And you get 64 bits from each of them. And this is operated in a ganged mode, let's say. Whenever you send the command saying read these 60, whenever you send the activate command, you really activate the same row in all of these different chips. And then whenever you send the read command, you get the read data for the same column in all of these different chips. And essentially, you get 64 bits from this chip in consecutive 8 cycles, as we've discussed, and 64 bits from this chip in consecutive 8 cycles. But in each cycle, you get 64 bits across the different chips. So 8 bits from each chip, but 64 bit across different chips. And over 8 cycles, you get 64 bytes. Okay? And this is clearly a DIMM. So you can see that DIMM is actually less costly because you can put more connections over here that can get connected to your slots over here. Okay, so hopefully that answers your question. Okay, let me continue. Okay, good. Let me actually say that that's on DIMM-based systems. But if you actually want to have a chip-based system, you can actually have do whatever I said, whatever you suggest actually, a 64-bit integer stored across 8 different banks and 8 different chips. You can also do that as well, right? In the end, it's all about data mapping and how you do the data mapping whenever you're designing the memory controller and your system. Okay, so I'm going to stop here in terms of the DRAM operation. Maybe actually I'm going to stop here and take a short break also before moving. Let me see the next slide first. But basically, we've covered the DRAM operation here. And if you really want to know more about it, there are a lot of papers written. And I would suggest the section 2 of this paper that we have recently written. And we tried to make it really accessible in this case. But okay, yeah, this is a good place to stop also. But I'm not going to take a very long break. So let's be back at 2:30 so that we can continue. But it's good to take a break than not take a break, I think. Then we will continue with the reasons for long memory latency. Okay, great. So this is where we left off. And I still recommend that you read section 2 over here if you want to get a very clear and crisp understanding of how DRAM operates underneath. But some of the other papers also have a similar background, but maybe they don't spend as many pages to explain it in detail, because usually conference papers are page limited. You cannot write as much as you really want to explain everything. Okay, let's go to the next slide. Okay, so basically with that background, hopefully you have a good understanding of how the underneath operates. We've seen this many times, but I think this was the most concrete from the very bottom up. So we're going to tackle the 2 latency inefficiencies that we've discussed. One is the design of the DRAM microarchitecture, and the other is the one-size-fits-all approach. So let's start with the first one. I'm going to give you examples over here. So this is, as far as I know, the first work that tries to provide a low latency, but also low cost architecture. So let me actually go back over here clearly. So one of the ways you can reduce the latency in DRAM is by reducing the length of the interconnects. And the real interconnect that matters is whenever you're sensing data through the sense amplifier. So whenever you're activating, for example, that interconnect actually is very long. Even though it looks short here, it's actually very long because these are 8,000 interconnects, 8,000 wires, let's say. They have to be very, very small, and they have to be long enough to span the distance of the furthest cell over here and the sense amplifier over here, right? So these interconnects actually dominate your latency. The longer interconnects are not that bad because these are much smaller. Keep it in perspective. It's only 64 bits. So you have 64 of these interconnects or wires, let's say. They have to be very large and they have to be very strong so that you can do the drive from here to there. Well, that's one of the reasons why they're only 64 bits. But their latencies are not as bad actually as a result. But the latencies of these very short interconnects are very slow. So if you really want to reduce the latency of activate, for example, you really want to reduce the length of that interconnect somehow. Now, what you can do is you can reduce the size of your subarray. So let's assume the size of your subarray is, I don't know, 1,000 cells. You get some latency value. If you reduce it to 512, let's say, you reduce your latency. Why? Because your interconnects are shorter now. That sounds good, right? No, it doesn't sound good because now you need to add more sense amplifiers. Right. If you want to keep the same capacity, in this case, let's say 1, 2, 3, 4 subarrays. So we have 4,096 rows. And to be able to work with those 4096 rows, clearly we have 2 rows of sense amplifiers. Now, if you want to reduce the size of your subarray to reduce your latency, what you need to do is you need to have 8 subarrays now, but you need to also double the sense amplifiers to 4. So your area cost increases clearly, right? Because you're doubling the sense amplifiers. And actually, as we will see in a little bit, the size of the sense amplifiers is very large. As a result, reducing the size of your subarray can reduce your latency, no question about that, but it comes at a high cost, because as you add more subarrays, you need to add more sense amplifiers also into the system. Okay, so that's one way of reducing latency, and people actually have done it. You can actually buy products that have low latency DRAM in it, but they use this technique. They reduce the size of the subarray. As a result, their area cost is very high. As a result, these DRAM manufacturers charge you an arm and a leg. It's very expensive, basically. These memories they're called RLDRAM, for example, reduced latency DRAM, or FC DRAM, fast cycling DRAM. And they're used almost exclusively by people who really, really care about latency to pay that much cost. And they're used, for example, in some backbone routers in the internet. And maybe some gamers use it also, but if they really want the experience. Okay, but okay, wow, this went too fast. Okay, so basically, let me go back. I've already said what I said, but let me actually go over here. So the question is, what causes the long latency inside the DRAM chip, right? As we've discussed, the data needs to get out of the cell array, and actually from the subarray itself, because the sense amplifiers are in the same subarray over here. And there's some subarray access latency that you need to have. And also, once you have the data in the row buffer, local row buffer, you need to bring the data with the read or write command, right? So there's some I/O latency to take it out over here. So DRAM latency is really subarray latency plus I/O latency, but usually subarray latency is dominant, as we've discussed just now. So why is the subarray so slow? Let's take a look at that. Basically, the interconnect is long. That's the major reason. So if you look at the subarray, this is another depiction, 2-dimensional array of cells, and this is the cell itself. You have a large sense amplifier. You need to have a large sense amplifier to, in order to be able to reliably sense a single cell. And a single cell is very small, as we've discussed, right? So usually the size of the sense amplifier is 100 to 200 times the size of a cell. Now imagine that. So what manufacturers do is they want to amortize the sense amplifier cost by having a long bit line. Let's say they string together 512 cells or 1024 cells in a single bit line. Now this leaves a small area, because think about it. In the extreme case, you would have one row and one sense amplifier, right? And the access to that row would be really fast, and your subarray would consist of one row. That doesn't sound good, because a sense amplifier is 200 times the size of a row. So you're basically wasting resources to get very low latency. That's the extreme case. So the manufacturers make a trade-off. They basically say, okay, we want to put 512 or 1024 cells, rows in a subarray. It's not extreme, but they also don't do 64,000 rows in a subarray. If they did that, the latencies would be even worse. And the reliability of those really long interconnects would be even worse. So they make a trade-off, and they say, okay, here's where we can amortize the sense amplifier cost while keeping, well, reasonable latencies, while keeping reasonable reliability. So this leaves a small area. But the downside is your bit line is much larger than one cell right now. It's spanning 512 or 1024 cells. As a result, a long interconnect has high latency and high power. Clearly, large bit line, because of the large bit line capacitance, right? There are a lot of things also hanging off the bit line, as you can see over here. So there's a lot of load capacitance on the bit line here. Okay, so that's the reason why it's slow. Okay, so clearly this points to a trade-off that I mentioned earlier. You can have a long bit line architecture that strings together 1,000 cells, let's say, per bit line. You can make it faster by chopping this up into smaller, shorter bit lines, as you can see. But now your area increases because you need to add more sense amplifiers, like we discussed earlier. Well, clearly you can make this smaller by consolidating the bit lines together, right, and reducing the sense amplifiers. So there's a clear trade-off between area and latency, as you can see, as we discussed earlier. But now you can see that it's manifested in a different way because of the sense amplifiers. And it's hard to break this trade-off, actually. if you come up with a technology that actually reduces both of them at the same time, then that's going to be either magic, or meaning you're ignoring some things, or you're really brilliant. Okay, so let's take a look at this trade-off a little bit quantitatively. So we did some simulation experiments. This is latency on the x-axis and normalized DRAM area on the y-axis. Normalized to, so as you go here, I'm going to talk about what's normalized to. It's the long bit line architecture, basically. As you go from top to bottom, you become cheaper. As you go from right to left, you become faster. So ideally, you would like to be somewhere here, of course, right? So this is commodity DRAM. It has long bit lines, let's say 512 cells per bit line. It makes a trade-off on the extreme right side, meaning it's cost optimized, right? As we've been discussing. Now, if you reduce the cells per bit line, your cost clearly goes up significantly, but your latency also reduces. And the fancy DRAM that I've discussed earlier reduces the bit line length, like FC DRAM, reduced latency DRAM. These make the trade-off of short bit lines, but they increase the cost. And the cost actually is not directly correlated with DRAM area. That's one thing that's correlated with. But as you increase the DRAM area by some amount, you get penalized even more. So there's a double effect going on over here. You increase the DRAM area, you clearly have more cost because of that. But on top of that, you get penalized more because the market becomes smaller. Well, according to DRAM manufacturers, this is, or yield becomes smaller, something becomes smaller. As a result, the manufacturing capacity also reduces. As a result, they charge you even more today. So these are more expensive than they need to be actually. Okay, that's because they don't want to reduce the latency over here actually. So this hopefully gives you some other mindset. This goes into a lot of business decisions also, in my opinion, but we don't need to go into that. There's a complex business going on here as well. But one of these are very expensive, not just because their DRAM area is higher, but because there's a smaller market that's envisioned, etc. Their manufacturing capacity is limited, etc. Okay, but our goal as scientists, I think, is to go here clearly, right? Whenever you have a trade-off like this, a good PhD thesis is really about achieving this goal or getting as close as possible to this goal, right? That's one way of actually deciding on a PhD thesis, for example, or master's thesis that you want to do. You see a curve like this and you say, oh, I'm going to reach here. Maybe in the end, you don't reach over there, but if you don't shoot for here, you will not reach there clearly, unless you're really lucky. Okay, so how do we reach there, basically? So let's start with, we're going to look at long bit line and short bit line. Clearly, long bit line has small area, high latency, some greens and some reds. Short bit line has low latency and large area, some greens and some reds. Whenever you see a picture like this, heterogeneity should come to your mind, right? As we've discussed, in hybrid memory systems, we had this sort of issue, right? So we start with the long bit line architecture to get the small area. And we also want low latency in it. The question is, how do we create it? And the idea is very simple. Create a small portion of this that has short bit line, that looks like short bit line. This near segment, as we will call it. And then the far segment will not look like short bit line. That's the idea. Basically, we would like to segment the bit line and isolate this part of the array from this part of the array by adding isolation transistors. And this is called now tiered latency DRAM. It gets small area using long bit line. Clearly, we have not increased the sense amplifiers at all. We added some area cost due to these isolation transistors, which we will talk about. Now, if you want to access this part with low latency, you turn off the isolation transistor, and this bit line looks short to the sense amplifier, right? So its capacitance is small. So you can access it with low latency. Now, if you want to access, well, I don't animate it over here, but if you want to access this part, data that's in this part, you enable the isolation transistor. Now this bit line looks long, so you have to pay the penalty of the high latency. But at least you have a portion of the subarray that you can access with low latency. Now this sounds great, right? Now this is the idea of heterogeneity applied at the granularity of a subarray level. You could also, at the granularity of within the subarray. You could also apply it across subarrays, which we will also discuss later on. You could have some subarrays that look like this, some subarrays that look like this. Okay, that sounds interesting now, right? And there's some other proposal related to that which we will talk about. There's some downsides to it. Here, you can move the data from here to here very fast. Whereas if some subarrays look like this and some other subarrays look like this, how do you move the data between them? You need to have efficient row clone, for example. But these are subarrays. Clearly, we know that row clone is not efficient between different subarrays of the same bank. Okay, and you can have different banks as well, different banks with different size of subarrays. Okay, I'm going to leave your imagination, leave it to your imagination to actually add different sorts of heterogeneity into the DRAM chip. But we're looking at intra-subarray heterogeneity here. A subarray can have a fast portion and a slow portion. Okay, so if you do this, these are the latency reduction that you get. So near segment, you can reduce the access latency by 56%. This bar is wrong. It's really 56% reduction, which should really be somewhere over here. And unfortunately, the far segment latency increases by 23%. Why? Because you have additional capacitance and resistance due to the isolation transistors. Whenever you enable the isolation transistors, they add resistance and capacitance. That's unfortunate, but that's how life is. Which means that you need to manage this memory really carefully. Okay, and commodity DRAM, you can see that at the time we looked at it was 52.5 nanoseconds for row cycling delay. This is back-to-back activates. How fast can you do another activate after one activate? Okay, this is the power. As I said, latency and power often go hand in hand. And in this case, we reduce the power of DRAM access by 50%, 51% for near segment. For the far segment, unfortunately, power increased by 49%. And overall, the area overhead is about 3% due to the isolation transistors. But isolation transistors enable you to switch between the fast portion, and the slow portion. Okay, I think this is a cool idea. And this is, when it was published, it was very novel, clearly. Clearly, there are a lot of other papers that were published related to it right now. But let's take a look at where this is. So a near segment actually breaks this curve, meaning, so in this case, we look at a near segment that has 32 cells per bit line. It takes us somewhere over here, as you can see, which is equivalent to somewhere around 32. But unfortunately, far segment, even though it has 480 cells per bit line in our experiments, it takes us farther away over here because of the additional resistance and capacitance of the isolation transistors. So now we have a memory that's heterogeneous inside, and we need to manage it somehow. So basically, how do we manage it? I'm going to give you some examples, not go into a lot of detail. This paper is one of those readings that you can potentially do as bonus readings in your next homework. But basically, it's a substrate that can be leveraged by the hardware or software. You can expose this fast part to the software also, well, near segment to the software, or you can expose the hardware only. So one of the ideas, let me give you a couple of potential cases. The near segment, the fast part, can be used as hardware managed inclusive cache to the far segment. That's possible. Or you can manage the near segment as an exclusive cache to the far segment. Meaning, so inclusive means that whatever is contained in the cache, meaning the near segment, is also in the far segment, meaning you're replicating data. Whereas exclusive means that whatever is contained in the cache is not in the far segment, which means that you're swapping data between them. Which means that exclusive cache is good because you're not reducing the overall memory capacity that's seen by programs, but maybe you have more management overhead because you're swapping, right? Inclusive cache, you're reducing the overall memory capacity seen by the programs. Or you can basically say, we have this fast portion and slow portion. Operating system, map the pages based on some profile information to these different segments. And this is certainly possible. And I think this is also a good way of using it, as long as you can do it this way. One thing that doesn't work is simply replacing existing DRAM with TLDRAM and hoping that the pages that need low latency or that are frequently used end up in the near segment. And this doesn't happen. As a result, by simply replacing DRAM with tier latency DRAM, you don't gain a lot of performance. Okay, so the paper explores these options, but I'm going to talk about the inclusive one, which is the simplest one. But it may not be the best one overall, but even it's the simplest one. So what does this mean? You look at a subarray. Now we have inside the subarray, we have the sense amplifiers, row buffer, the near segment, closest rows to the row buffer, and then the far segment. And we're going to treat far segment as main memory, whereas near segment is just a cache that's close to main memory. It could be a cache with 32 rows, for example. So it's a very large cache. It's a row-based cache also. Right? So there are multiple questions. Both of them are easy to answer, really. The first one is how to efficiently migrate a row between segments, and the second one is how to efficiently manage the cache. So the first one, we already know actually by doing row clone. That's the answer here. So but this paper was actually published slightly earlier than row clone, and the goal is really not row clone. This is a mechanism to do the row clone, as you can see. Basically, the idea is to migrate the source row into destination row. How do you do that? Essentially, it's 2 back-to-back activates. So naive way, you don't want to do that, as we discussed. So the way is connect these things directly. So how do you do that? Transfer data from source to destination across shared bit lines concurrently using by activating the source row first, which brings the data into the row buffer. And then you activate the destination row and connect the cell to the bit line. That's the idea. So this is a form of row clone, and you know that it's fast. So, okay, that's how you can actually move. Whenever you access a row in the far segment, you may want to actually bring it into the cache so that the next time you access it, the access would be fast. That's the idea. Now, that's how the cache works. So how do you efficiently manage the cache? This I'm not going to go into. This entails many questions clearly, right? Which rows do you bring into the near segment? Do you bring, every time you touch a far segment row, do you actually bring it into the near segment? What kind of metadata do you need to keep to facilitate that? How do you manage the rows in the near segment? Let's say you have 32 rows. If they become full, which one do you kick out? And now kicking out may be not so costly if the near segment is not modified. The row is not modified in the near segment. If it's modified, you need to write it back to the far segment. So it's essentially all the issues related to a cache. So you need to manage it well. So if I'm going to show you results with even the least management, meaning least recently used management. Whenever you access a row in the far segment, you bring the data into the near segment. And the eviction from the near segment to the far segment is done using a least recently used policy. Basically, least recently used row is evicted whenever you need to evict something to make room for something else. So clearly, you can do much better, actually, than this that I'm not going to talk about right now. But if you do what I just said, even then you gain a lot of performance. Basically, you get more than 10 to 12% on different types of systems, average across many workloads. And you actually reduce power consumption, DRAM, this is DRAM power, significantly, more than 20 to 23%, as you can see over here. Okay, so I'm not going to go more into detail of this, but you can read the paper. But one interesting thing is the trade-off between cache near segment length and performance. So near segment length is how many rows you have in the near segment. It's called cells over here, but it's the same thing as rows in this case. But as you go from left to right, you get larger cache capacity, but also higher cache access latency. With one single row, your access latencies are lower. But you can see that the sweet spot is somewhere over here at 32, where we tested. You get the highest IPC, instruction per cycle improvement over here. Okay, but very interesting to see that even one row of cache buys you significant performance. This is average across many workloads, as you can see. Even one row of cache buys you a lot of performance. If you go to 256 rows, your cache is very large, but access latency is also very large. As a result, you lose performance. And maybe when your cache becomes large, you don't gain a lot of performance anyway, because you may actually exhaust the locality that you need. So one of the reasons why a lot of these mechanisms gain performance is because of bank conflicts, which we're going to talk about later on. And the idea is you need something from row A, and then you need something from row B, and then row A, and then row B, and then row A, and then row B. So you clearly have a bank conflict in this case. You're ping-ponging between A, B, A, B, A, B. Now, if you have a single row buffer, clearly you need to, you're really thrashing your row buffer, fine. But if you actually use tiered latency DRAM with one row, you cache either A or B, and then you reduce the latency to them the next access rate. But if you cache both of them, then you reduce the access latency to both of them, as you can see over here. So these bank conflicts are reduced. Their impact is reduced with mechanisms that look like this. Okay, so if you want to learn more, you can read this paper. And this paper also has a very clear background section on DRAM, and I would recommend that. Okay, any questions? I guess I will keep going and people can ask questions. So we discussed this idea earlier, Lisa. I wanted to discuss it in a little bit more detail over here, because I think this is a really important way going into the future. But as you know, bulk data moments is a key operation in many applications, and going through the memory channel is way too slow for this. If you want to do a 4 kilobyte page copy, for example, from source to destination, right? It's long latency and high energy, as you can see over here. And that was one of our motivations in this work. So clearly, if you move data inside DRAM, if you want to copy data between one subarray to another subarray, you have to go through the internal data bus in DRAM, because these subarrays are not connected as we've discussed in the past. And that takes a long time. And this is because there's low connectivity between the subarrays. And it's a fundamental bottleneck for bulk data movement. So our goal here was to provide a new substrate to enable wide connectivity between subarrays. So remember, tiered latency DRAM has wide connectivity within a subarray. You can turn on and off in isolation transistors, right? And that gives you higher performance. Here, we're going to be able to connect different subarrays, and hopefully that will give us performance in different ways. Okay, so that's the idea over here. We have isolation transistors between two subarrays like this. So it's very similar to tiered latency DRAM, except you add the isolation transistor across different subarrays. So in a sense, very, very different from tiered latency DRAM, right? You're not trying to reduce the latency of a segment in a subarray. You want to connect these subarrays such that you can move data between one subarray to another in a faster way. So this leads to many, it's a versatile substrate that leads to many applications actually. Bulk data copy, as you can see. In DRAM caching, we're going to talk about a little bit, and fast precharge. So I'm going to talk about these in a little bit. I already mentioned the slide earlier when we talked about row clone, but let's go here first. So to be able to use this, you need a new DRAM command. So you need to change the interface a little bit. And as we discussed at some point, changing the DRAM interface is one of the hardest tasks in the world because there's so much conservatism in the DRAM interface. Their mindsets are very fixed, and it's terrible, I think, overall. It limits a lot of innovation in our systems that could have happened by now, many, many times, actually. But basically, this is the command, row buffer movement. The idea is to move a row of data in an activated row buffer to a precharged one. So you can see this is the subarray 1, subarray 2. These are the isolation transistors that we add. These are the sense amplifiers and the precharge units. We look at them separately, but they're part of the sense amplifiers, as you can see. So, okay, let's assume that we want to copy one row from subarray 1 to subarray 2. We first activate that row in subarray 1, which brings the data into the sense amplifiers of the subarray. And then, I mean, you can see that this subarray's bit lines are VDD and the subarray's bit lines are not precharged. Now, we issue this row buffer movement command, which moves data from subarray 1, which is the sense amplifiers of subarray 1, to the sense amplifiers of subarray 2. So what does it do? It basically enables the sense amplifiers. It turns on the sense amplifiers, and once you turn on the sense it enables the isolation transistors. Sense amplifiers over here are enabled. Over here, they're disabled, as you can see. Once you turn on the isolation transistors, now this bit line gets connected to the sense amplifiers over here, and they have charge sharing, and as a result, this also becomes VDD, and they amplify the charge, as you can see. Now this subarray sense amplifiers also contain the data that is contained over here. That's the idea. Now, what you can do is now you can activate some row over here, which brings the data over here after turning off this one, of course. Well, you don't need to turn off that one, actually. You can just activate a row over here, which brings the data over here. So by doing activate here, and then row buffer movement, and then another activate here, you can copy data from this subarray, this subarray's row, activated row, to this subarray's activated row. That's the idea. Clearly, this transfers an entire row between subarrays, right? And you can actually increase this. You can actually do this across 3 subarrays. You can connect 3 subarrays like this. You can actually keep connecting more, but then if you keep connecting more, you have a problem because what happens is your interconnect becomes longer, right? As you keep enabling more isolation transistor at the same time. So we limit that. We basically say, if you want to go from this vicinity of subarrays to the next vicinity, you actually need to use another row buffer movement command. So you need to enable the sense amplifiers again. You can enable these sense amplifiers with a single command. Okay. And then you can transfer from subarray 1 to 2 and 3, or directly from 1 to 3. Okay, you can read the paper for validation, etc. You can see that you can transfer 4 kilobyte data in 8 nanoseconds, even considering the guard bands that are taken into account to ensure reliability. So this is actually a very significant bandwidth. It's 26 times the bandwidth of a very high bandwidth DDR4 channel. And the area over it is very small. It's just these isolation transistors. So let's take a look at the applications a little bit more. Basically, this is called rapid inter-subarray copying. It's row clone across subarrays, but using Lisa substrate. So the idea is what I told you. You activate the source row, which brings the data into the row buffer or sense amplifiers of the source subarray. And then you do the row buffer movement command, which brings the data into the sense amplifiers of an unactivated subarray 2. And then you activate destination row, which brings the data from these sense amplifiers, which are strong, and they drive the destination row. So activate, roll buffer moment, activate. That's the copy that you need to do across close by subarrays. If you're farther away, then you need to do multiple roll buffer movement commands. Activate, roll buffer movement, roll buffer movement, roll buffer movement, and then activate, right? Okay, as you can see, this reduces row copy latency significantly and DRAM energy significantly, getting closer to intra-subarray. Clearly, you cannot be as close to intra-subarray, because if you want to do the intra-subarray, it's activate, activate, right? And you're not exercising long interconnects. So we just add an row buffer moment and a longer distance here. So that's why it's not as high as row clone, but it's not bad. If you remember, row clone was reducing the row copy latency by 11.6x, I think. Now this is 9.2x, which is not bad, getting closer to 11.6x. And I think row clone was reducing DRAM energy by 77.4x. Now it's 48.1x, which is not bad again. Okay, so the second use case is in DRAM caching. You can reduce DRAM latency with low area overhead. So as we discussed, you get the long bit line architecture and short bit line architecture. The question is, can you get the benefits of both? As you can see, this paper quantifies it. You get high area overhead if you go to a short bit line architecture. We don't want that. So we want a heterogeneous DRAM design, like tiered latency DRAM or the heterogeneous subarrays. So we're going to look at the heterogeneous subarray design over here, which was introduced by this paper at ISCA 2013. The idea is to add fast subarrays as a cache in each bank. That looks like this. In Figaro paper, you already got mentioned. Actually, Figaro outperforms all of these works, but I think it's good to go over them again. Basically, you have a slow subarray and a fast subarray. Fast subarray is clearly a smaller number of rows. That's why it's fast. And the challenge is, if you use it as a cache, you need to move the rows from a slow subarray to a fast subarray. The question is, how do you do that today? If they're not connected to each other, well, you cannot do it easily. So you need to rely on software to do profile-based mapping. And that's essentially what the people who introduced the idea did. And they showed good results. But this LISA work that we did enables a much better substrate by doing this dynamically. Basically, if you actually have these isolation transistors between slow subarray and fast subarray, you can cache rows from a slow subarray to the fast subarray very quickly, like we've discussed earlier. And this reduces the hot data or cache access latency by 2.2x at only small area overhead, as you can see. And the performance benefits are significant, but you can read the paper. So I'm going through this relatively quickly because you've seen the ideas in the Figaro presentation. And if you haven't watched this Figaro presentation, please take a look. That was part of the lecture in lecture 9 last Friday. Okay, so the next use case, once you have this sort of interconnectivity across subarrays and DRAM, you actually have a lot of possibilities. And this is the next use case. It's called linked precharge. The idea is to, well, the problem is the precharge time is limited by the strength of one precharge unit. So the P units over here are precharge units. So whenever you want to precharge a subarray over here, you turn on the precharge units of that subarray, and it takes time. Now, linked precharge, the idea is because you have isolation transistors over here, you can connect the precharge unit of another subarray to the precharge unit of the neighboring subarray. And you can precharge using multiple precharge units as shown in this picture over here. So 2 precharge units drive the bit line, the same bit line. As a result, you can precharge much faster. And both of them can turn on, as you can see. And much faster means you can reduce the precharge latency actually very, very significantly by 2.6x. I believe this goes from 13 nanoseconds to 2.5 nanoseconds. That's exactly 2.6x. Even while preserving a significant guard band in terms of latencies, which we're going to try to eliminate later on in the rest of this talk, in lecture. Okay, so hopefully this is clear. This is LISA, and you can have more information about it. It can enable fast inter-subarray data movement in DRAM. Any questions? So I'll keep going, I think. I think in one of the earlier lectures, we also talked about network on memory. That's a much more recent idea. I don't have slides over here that are prepared, but I would also encourage you to take a look at it. So that solves another problem with row clone, if you remember. The bank-to-bank interbank transfers are costly because you cannot do anything else. While you cannot transfer data out of the chip if you're transferring data between one bank to another. And this idea of network on memory actually enables you to transfer data out of the chip or into the chip while you're actually doing copy between 2 different banks. Of course, this is applicable to a 3D stacked memory. You have a logic layer. This way, you can interconnect the different banks in a much more flexible way compared to the shared internal bus that you have in an existing DRAM system. But I think this work also goes to show that increasing interconnectivity in DRAM is a good idea. So let me actually stop sharing, and I'd like to share that work very quickly, but I'm not going to take a lot of time, frankly. Maybe I made the mistake of stopping sharing, but I guess we will see. Okay, let me actually start sharing. I'd like to point you to that work. Okay, you can see it, right? Okay, I can see it. That means hopefully you can see it as well. Okay, I have to search. Wow. Somehow I'm not able to. Okay, I just need to search for network. There are a lot of network. Wow, interesting. Okay, yeah, this is the paper that I'm talking about. And I would recommend looking into it also. It's a short paper if you're interested, of course. It basically proposes a network in the logic layer so that you can actually, you can actually transfer data between banks in a much faster way without preventing any bank from transferring data outside of the DRAM chip. That's the idea. And this actually leads to significantly higher performance than row clone whenever you're transferring data between banks. That's the idea. So you can take a look. I'd recommend taking a look for sure. I'm going to stop sharing and go back to, I need to start sharing again, which is interesting. Okay, so these ideas are actually increasing interconnectivity in memory. And I think this is really important going into the future, looking at different ways of increasing interconnectivity within a subarray, across subarrays, across banks, and across different memory components is really, really important because we're really lacking in interconnectivity actually. And I think this is one of the huge downsides of existing memories compared to, for example, a human brain. If you look at a human brain, there's a huge amount of connectivity between neurons, whereas we don't have that sort of connectivity in our memories today. And I think all of these works are in the right steps. So they're taking the right steps, going in the right direction to increase the connectivity. So it's good to, I think about this maybe in your leisurely time. How can we get closer to the connectivities that we have in real systems? Real systems meaning maybe natural systems. I think we're not there yet. So let me go over this idea, a couple of other ideas really quickly, because these are state of the art, and hopefully those will give you some idea of where we are. Okay, so this work, Crow, was presented last year in ISCA, and it tries to solve 3 challenges of DRAM scaling: access, latency, refresh overhead, and exposure to row hammer vulnerabilities. I'm not going to talk about all of them in very detail, but if you look at a conventional DRAM, you already know how it works, right? The basic idea is this. Instead of having in a DRAM subarray having a single row decoder, enable some area that can be accessed with another row decoder. So this looks like tiered latency DRAM to you, right? Yes, at some level, yes, but it doesn't have the isolation transistors, and that's a key innovation. Basically, you have this bit line. It's not segmented. There are no isolation transistors, but you can access. You partition it into regular rows and crows, copy rows. That's the idea. Now, this substrate using row clone type of operations can enable you a lot of powerful caching mechanisms. Okay, let's take a look. So basically, one of the operations, row copy, you activate this row, and then you activate a copy row. You copy a regular row to a copy row. So you could use this as a cache. Now, the second operation you could do is multiple row activation. You concurrently activate these 2 rows. Now, if you do that, assuming you store the same data in each row, access latency would be much faster. Why? Because you're doing the perturbation much faster, because now you're using 2 cells instead of 1 cell. And as a result, everything becomes much faster. We verified this using SPICE simulations, etc. But that's the idea. Basically, the idea is dual row activation over here. We saw triple row activation, if you will. That was the ambit. We saw back-to-back activation, which is the row copy. And dual row activation enables you to access the same row or same data much faster, assuming you already copied it inside this crow area before. That's the idea, basically. So clearly, you can use the crow cache to reduce access latency. What you can do is you basically copy a row that you access here into here. And then the next time you access that row, you do multiple row activation, dual row activation, which is much faster. Or you could do this, you could use this as crow ref, So you can remap a weak row to a strong row over here and mark the weak row unusable, and you just access the strong row. That's the idea over here. Or you can use a mechanism for protecting against row hammer, which I'm not going to talk about over here. Basically, the idea is actually very simple. You detect a row hammer attack somehow, and you remap a row hammer vulnerable row to this copy row area. And you can use all of these concurrently at the same time. And if you look at the paper, there are good results by using caching and reducing refresh rates using what I discussed, by remapping weak rows, weak from the retention time perspective, weak rows into the copy row substrate. You can get significant speed up and significantly less DRAM energy. And the hardware overhead, you can see that's one of the big benefits compared to tiered latency DRAM. So tiered latency DRAM, yes, it can reduce latency, but it cannot do much with refresh without a lot of modification. So this actually helps with refresh, as you can see. So you can see that the hardware overhead is also much lower than tiered latency DRAM. And you can read the paper for more detail. If you're interested, take a look. I'm going to briefly talk about one other work. Actually, Hao Song, who is one of the students who's taking this class right now, he did an internship with me for 9 months, I believe, last year. And he was inspired by a lot of these DRAM latency works. And he said, I could do better than Crow, or I could do a better mechanism, I believe. And he came up with this better mechanism, which I think is really the state of the art today. It's called CLR DRAM, capacity latency reconfigurable DRAM. And at some point, he's going to present this also as part of as part of something similar to what we did last week. But let me give you the key ideas over here. I believe this is really the state of the art in terms of reducing latency in DRAM, and was published in last ISCA. And again, the goal is to reduce latency when you want it, but also keep the capacity when you want it, right? And existing DRAM systems make static capacity latency trade-offs at design time. And for example, tiered latency DRAM has a static near segment, right? Crow has a static copy row area. These are all static. Even though they're low cost, they're static. So you cannot have the entire DRAM to be low latency with these mechanisms whenever you need it or you want it. Or you cannot have the entire DRAM for high capacity. You cannot have the extremes, and you cannot have a lot of points in between, basically. As a result, you cannot adapt to the main memory capacity and latency demands well. And the goal here is to design a low-cost DRAM architecture that can be dynamically configured to have high capacity or low latency at a fine granularity, at the granularity of a row. So basically, for a given DRAM row X, we should be able to choose between high storage capacity operation and low latency operation. And that the idea of capacity latency configurable DRAM is exactly that. It's a low-cost architecture that can enable a single DRAM row to dynamically switch between max capacity mode and high performance mode. And the key idea is simple. In hindsight, these ideas hopefully should be simple. You dynamically configure the connections between DRAM cells and sense amplifiers in the density optimized open bit line architecture. So let's take a look at it. So basically, this is what we have in existing architectures. I didn't want to complicate things, but we'll go over this later on when we talk about CLR DRAM. But basically, each bit line is really connected to only one sense amplifier on one side. So this is one bit line. It's connected to the sense amplifier here. There's another bit line. It's connected to the sense amplifier over here. So that's how really the subarray operates in today's systems. Whatever I showed you earlier was an abstraction. Even that was an abstraction. Internally, the subarray operates like this because you really need to have the sense amplifier really span multiple lines, multiple bit lines over here because it's too big. And this is how you compact many things. And this is how you can enable other subarrays to be connected to the same sense amplifier also. I'm not going to go into the details, but this is how things are implemented today. So you can see that cells A and B in this row are connected to different sense amplifiers. So we're going to take advantage of that actually. So CLR DRAM, what it does is it enables configurable connections. So you can see these are isolation transistors again. The isolation transistors that we've seen, they're exactly the same as those isolation transistors. But now we have different types. So depending on how we enable these isolation transistors, it's going to look exactly like this, or it's going to be low latency. Let's take a look at it. So let's take a look at max capacity mode, for example. To be able to mimic the open bitline architecture, we enable isolation transistors that are here. As a result, this system operates exactly like the baseline architecture, so it's very capacity optimized. So you get the same storage capacity as the conventional open bitline architecture. You don't lose capacity because you don't dedicate any rows, as you can see, to low latency access. But of course, there's some overhead, which is the overhead of these sense amplifier isolation transistors. Okay, in high performance mode, we do something different. Basically, we enable all of these isolation transistors that are marked in green. Now, what this does is it enables these two cells to be sensed by both by the same sense amplifier. Now, we also do is store this cell and its complement consecutively. Instead of storing separate values, A and B, we store one cell and its complement to encode one data value. That's the idea. Now, by taking advantage of the fact that both cells driven with different data values, they actually can be sensed by the same differential sense amplifier. This sense amplifier operates much faster because you're feeding in two values that are differential and that are essentially the same value. They're the complement of each other, right? And the sense amplifier is now much faster. So that's the idea over here. These are called coupled cells, and you use them to drive both sense amplifiers. So you couple the sense amplifiers also. And as a result, you get much faster operation. You get reduced latency and reduced refresh overhead with this coupled cell and sense amplifier operation. So the key results, very quickly, you reduce the latencies a lot. And again, as I said, this is the state of the art, I believe, in reduced latency, low cost DRAM. You see significant latencies, and you can read the paper for more detail. And the system level benefits, so these are verified using SPICE simulations, circuit simulations, and you need to evaluate the system level benefits using simulation. And these are some system level benefits, assuming some fraction of rows are enabled for low latency. Of course, there's more work to be done, and Hao Song at some point may talk about them. But now you can take a look at the paper if you're interested. Okay, so I think very quickly I brought you to the state of the art in low latency memory. There's more to be done in this area, and I think there's more definitely needed. If people have ideas, I'm always open to them. But you can see the importance of the topic, and there will be more things coming. Let me give you a little bit of history before I move on to the other part. So this is actually what the first work that we did to reduce latencies. I said tiered latency DRAM, yes, but the Subarray-level parallelism work is also very, very important because this tries to parallelize accesses to different subarrays. Since we've been talking about subarrays, I think it's good to see how this works. And this may also give you a good idea of how subarrays exactly work internally as well. So, okay, the problem is essentially bank conflicts are costly for performance and energy. They lead to serialized requests and wasted energy because they trash the row buffer, as I said, and they cause busy waiting. So we wanted to reduce bank conflicts without adding more banks at low cost. So there are two observations that this work takes advantage of. And the first observation is that a DRAM bank is divided into subarrays, and each subarray has its own local row buffer, as you've seen already. So as you've seen, this is our earlier picture in 2011 or so. This is a logical bank. It may have 32,000 rows and one row buffer. That's not how it really works. This is an abstraction. The physical bank actually divides 32,000 into 64. Now this becomes 512, right? Rows here. And each of them has a local row buffer. And then you have a global I/O, as we've discussed also. Why? The reason is this is, we already discussed the reason. This is too long of an interconnect to be reasonably low latency and also reliable, whereas this is short enough of an interconnect. Okay, so the second observation is these subarrays are actually mostly independent today. So let's take a look at it. So the way these subarrays operate, you have a global decoder for row decoder and a global row buffer, which is the global bit lines and the global I/O. So these are the places where subarrays are dependent on each other. So if you actually reduce the dependence in hardware between subarrays in these two structures, maybe you can access them in parallel as much as possible. And that's the idea. Why do you want to access them in parallel? Let's say an access goes to subarray 1. Today, if another access goes to subarray 64, it has to wait for the entire bank to become free, even though it could have been serviced in parallel, mostly, if we had actually enabled that parallel access, right? That's the idea. So if two consecutive accesses goes to subarray 1 and subarray 64, we would like to mostly overlap their access latencies. That's why this is about latency in the end. So the key idea of SELP is to minimally reduce the sharing of these global structures to enable back-to-back access to subarrays, different subarrays. So we would like to share the global decoder. Doing so enables almost parallel access to subarrays. If you reduce the sharing of the global row buffer, then different local row buffers can be active at the same time. That way you can actually utilize multiple local row buffers, and you will see that in a little bit. So this idea is actually, these ideas have been quite powerful. The paper that I'm going to mention that actually, the paper that I have been mentioning that was written by Intel and Samsung, one of the reasons why it was written was actually to promote this idea so that it goes into the DRAM standards at the time. Unfortunately, it didn't make it to the DRAM standards because there was a lot of political discussion clearly in the DRAM committee. And some people thought this was high cost for them. And clearly this increased the cost a little bit, but I don't think it increases as it increases as enough to actually kill the idea. I think some people just find it inconvenient to do nothing and to keep business as usual. Because that's how they make money, right? Why do you want to do anything if you're making money? That's when innovation stops, right? When you don't care about anything else other than making money, and if you're making money well. Okay, enough of that. But that's the reason why it's not in existing systems. But Intel and Samsung wrote the paper to push the idea into the existing systems, and even these two powerful companies were not powerful enough to push the idea into the DRAM standard. So that shows you how difficult it is to push things into the DRAM standard, which is, I think, a problem. It should not be that way. Okay, so let me go into the SALP idea a little bit more detail. Basically, these are two subarrays. You can see many subarrays also over here in the ... So what happens is whenever you activate a row, you send a row address, and that row address gets latched over here. So that row address drives all of the subarrays. Clearly, only one row will be activated, right? Because only one row can be selected depending on the subarray. The idea is to push these latches to be subarray level. So clearly, if you have only one latch, you can latch one address, and you can enable only one subarray, only one row in the entire bank. But if you have multiple latches, then you can latch one address here, activate one row, and then you can latch another address over here, activate another row. And you can overlap the activates to these different subarrays. That's the idea, right? So it's very simple, as you can see. We're pushing this global latch to be local latches. And there is enough space in the DRAM chip to be able to do that. Now you can concurrently, if it's possible, activate both rows. But to minimize the modifications to the standard, you actually activate one row first, and then the next row in the next DRAM cycle. Okay, so hopefully this is clear. The second one is looks like this basically. So today in a DRAM, if you want to read data, whenever you send a read command, all of the subarrays get connected to the global bit lines. That's how it works basically, to minimize the area cost. Now clearly this doesn't work if you want to have multiple rows active in different subarrays, because if one row is active in this subarray, if another row is active in this subarray, and if both of them get connected to the global bit lines to get the data out whenever you do a read, or to get the data in when you have a write, you have a problem because both of them will drive the global bit lines, and as a result, you get a short circuit in the global bit lines, right? Because you cannot have well, if you have multiple drivers, the result is not good, basically. You could even burn the circuit depending on how it's designed, right? So the idea here is to add a simple switch so that you can designate which subarray is going to drive the global bit lines. So assume that you're reading from blue subarray. You have a designated latch, which designates which one you're reading. So the read command goes to the blue subarray. This designated latch connects this local row buffer to the global bit lines, and you get the data out of the global I/O. Now, we depict this like this, but these are actually on top of each other. So the global bit lines are actually on top of this. But to be able to ease the understanding and animation, the global bit lines are pulled out over here in this animation, as you can see. Now you can keep multiple row buffers open in different subarrays. Now we access the blue row in the blue subarray. We can turn it off with a command, and then we can read the yellow subarray while this is active. Now, if you need to do another read from a blue subarray, you can do that. You can go back and do the read to the blue subarray again, and then you can go back and do the read to the yellow subarray. So if you have a bank conflict, you can switch between these two subarrays very easily and very quickly without doing activates again, because both of the row buffers are active. Okay. Okay. So I think this is a cool idea, as you can see. So basically, what this does is from the baseline bank organization that looks like this, you move it to a bank organization that's slightly different. It's not really changing the entire bank organization, as you can see. And the overheads are the global latch and the designated bit latches and the wire to selectively enable a subarray. Not the global latch, the per subarray local latches, sorry. And the overhead is very small, 0.15% according to our calculations. And let me give you the results very quickly. Basically, this leads to significant DRAM energy reduction because it reduces the row buffer conflicts significantly, as you see over here, 19%. And it improves system performance by 17% in the most aggressive implementation. So in the paper, we propose 3 implementations. The most aggressive is MASA, multiple activated subarrays. But you can also do very simple implementations where you don't do the some of the modifications that we discussed. Then you gain less, of course, but you still gain a lot. And the ideal is the ideal performance benefit of making all of the subarrays independent of each other, meaning making all of them banks. So we're within 3% of the ideal, as you can see over here. So I think this is a cool idea. And the DRAM die area overhead is 0.15% versus 36% overhead with independent banks. Because if you have independent banks, you need to replicate the row decoder and the sense amplifier. Okay. If you want to learn more about SELF, you can take a look at this paper. It's also one potential bonus reading that you can do. But if you also want to learn more about SELF, you can read this paper from Intel and Samsung. In one of the sections of this paper, these folks discuss SELF. So basically, one of the things they say is write latencies are increasing because of technology scaling issues. And we can actually improve DRAM yield by increasing the write latencies. But this reduces our performance. For example, they say that by increasing the write latency by 5x, we can reduce the failed bit counts by 1 to 2 orders of magnitudes. Because if you keep the write latencies at smaller latencies we have today, they cannot write very well, meaning some of the bits will not be written because the technology node has a lot of resistance in the contact between access transistor and the capacitor. You can read the paper for the explanation. And they say we can actually overlap the write latencies by doing subarray level parallelism. And this is a limited use of subarray level parallelism. You can see allows a page and another subarray in the same bank to be opened in parallel with the currently activated subarray, and results in performance gain by increasing the row access parallelism within a bank. And they say we use it to compensate for the performance loss caused by the TWR relaxation. And they show some simulation results completely independent of us. And they show a lot of benefits, basically. Basically, they say that when TWR is relaxed by 2x to 3x, and SELF is applied within just 2 subbanks, just 2 subarrays over here, performance is even improved compared to the baseline. So SELF actually doesn't just compensate for the reduction, for the increase in write latencies, but also improves the performance compared to the baseline. So this is actually a very nice independent validation of the paper that I mentioned. And I already gave you the story. These folks at Samsung and Intel really wanted this inside the DRAM standard. And unfortunately, they got outvoted in a very political voting battle, let's say, in the standards committee. And as a result, you don't have this beautiful feature in your systems, and you can blame, you know whom to blame for not having this feature. In fact, a lot of the GPU architects really want this feature because in GPUs, what you do is usually you have a lot of bank conflicts. And if you're able to keep active multiple rows per bank in a GPU, you can get a lot higher efficiency and a lot higher performance with something like SELF. And when we evaluated SELF, we actually saw a lot of performance benefit in applications that are streaming. You can see actually over here in their results also, these are results from Samsung and Intel, not even our results. This libquantum is a very streaming application. You can see that the performance benefit of SELF is very high compared to their results. These are their results, of course, and this is a limited form of SELF. Keep that in mind. It's not the MASA, it's not the most aggressive form of SELF. Okay, so I think this is a good place to switch gears and talk about this one-size-fits-all approach. Any questions? Okay. Okay, So I'm going to switch gears right now and talk about this one-size-fits-all approach to latency specification. We've talked a lot about DRAM microarchitecture, and all of these previous ideas try to change the DRAM microarchitecture to reduce latencies. Now we're going to talk about something totally different. Can we fix the one-size-fits-all approach? And I call this tackling the fixed latency mindset. So reliable operational latency of any memory, actually, not just DRAM, but any memory, is very heterogeneous. By the way, all of these ideas that I mentioned over here earlier are not just limited to DRAM. They're all applicable to all sorts of memories, actually. And I've seen a lot of papers that apply, for example, Subarray-level parallelism or something like tiered latency DRAM to phase change memories going into the future. So memory at some level is very fundamentally similar to each other. As long as you know how to apply a general idea like Subarray-level parallelism or tiered latency DRAM or some of the other ideas that we discussed to other memories, you can do it. So in flash memory, you can apply some of these ideas also, I believe. But keep that in mind, actually. We're giving examples from DRAM, but by no means these ideas are limited to DRAM. Even SRAM can benefit from a lot of these ideas. For example, segmenting the bit lines is a good optimization to do in SRAM to improve performance. Okay, so the ideas that I'm going to describe are also going to be applicable to DRAM. All of the memories have some sort of fixed latency mindset, whereas reliable operational latency is actually very heterogeneous. What do I mean by this? The reliable operational latency, if you want to determine it, is very different across temperatures, across chips, across parts of a chip, across different voltage levels, etc., etc., etc. Now, clearly, we don't have time to cover all of these. I'm going to give you some examples of this. So the idea that I'm going to describe is to somehow find out and use the lowest latency one can reliably access a memory location with. And ideally do it dynamically, online, if it's possible, of course. But if it's statically, you could also potentially make use of it, like these gamers are doing, as we discussed earlier, right? So I'm going to give you a bunch of ideas over here. I'm not going to talk about all of them. But we're also going to look at interesting use cases where you can actually use the reliability latency trade-off to improve security or design security support in DRAM or main memory, like by enabling physically unclonable functions, and also latency true random number generators. So I'm going to talk about some of these, but we won't have enough time to talk about all of them. Some of them may be deferred to some lectures. But the key is we would like to find the sources of latency heterogeneity and exploit them to minimize latency and maybe create other benefits, as opposed to taking it for granted that DRAM latency or memory latency has to be fixed. Again, the reason it has to be fixed, I'm going to give you in a little bit, is a human dictated reason. Some humans said, this is the latency, obey it. But as scientists, it's always a good idea to critically think and question, right? Why should I really obey this latency if it's not really needed, right? Especially if I want low latency. So you should always ask the question. That's why science doesn't really go well with dogma, as we've discussed earlier, right? Dogma says obey it, and science said, no, let me think. Let me critically think. Okay, so let's look at why this is dictated, right? So let's basically, I said that latency is heterogeneous. So this is one form of heterogeneity. So on the x-axis over here, we see low latency to high latency to the right. And I basically depict which DRAM chips fall into which category. For example, DRAM chip C, because of manufacturing variation, it has to be accessed with high latency because its cells are slower by nature, let's say. We'll see what it means to be slower. It may have less charge. It may have a very slow access transistor. It may have some other problem that increases the latency. It's all about process variation in this particular case. Whereas DRAM A can be accessed with much higher latency because its cells are faster by nature. They can store more charge. We're not even talking about operating temperatures over here. We're talking about natural process variation. Okay, and within a DRAM chip, you can have a distribution also. Some DRAM cells inside DRAM A have to be accessed with high latency because they're not good enough for low latency access. Their access transistors may be too slow, for example. Some DRAM cells, on the other end, can be accessed much, much faster because they're good enough to be accessed reliably with low latency. So you can see there's a huge variation, and I'm going to quantify that variation later on with some of the works in the adaptive latency DRAM work to begin with. But let's take a look at what is done today. Well, I already said this basically because some DRAM cells are slow. Basically, today, latency is high because somebody specifies in the DRAM standards. This doesn't reflect the true DRAM device or cell access latency. We get latency variation because of imperfect manufacturing process, as I've discussed over here. And manufacturers choose a high standard latency to increase yield. So, okay, let's say if they chose the standard latency over here, right? What would happen? Well, they cannot sell DRAM chips B and C, right? Assuming they have the same mindset of using one single set of latencies. Well, what do? They make their life easier, meaning they choose a standard latency to be very high, and almost all of their devices are now acceptable. Like they can maximize their yield. Now, clearly from a business perspective, this is smart. Well, maybe not so great for innovation perspective as we discussed, but this is smart from maximizing your business and profits perspective, maximizing your yield perspective. Okay, but this clearly creates a huge timing slack for DMA. Whenever for the user who owns DMA, they're basically paying a lot of latency penalty, even though they could access DRAM much faster, right? And even within the device, for these cells, they could access them much faster. They're paying a huge latency penalty. The question is, does it really make sense to have this standard latency over here? So clearly, if you see this picture, assume that this picture is true. I'm going to show you some experimental data that proves that it's true, actually, many experimental data. That's why these gamers are fascinated by it, and the gamers are doing it also. But you could also use two standard latencies, right? I mean, this is a smart way of doing things, I think. Standard latency 1, standard latency 2. And then you can bin the chips and sell them based on different bins. The chips that can pass the standard latency low, let's say, they're sold more expensively. You could do that. And the chips that do not pass, but that pass standard latency high, they're sold a little bit less expensively. If I was a smart business owner, I would do this, I think. Clearly, this increases the testing costs of DRAM manufacturers, as we will also discuss. I mean, this doesn't come for free. Nothing comes for free in the world. Somebody needs to pay the testing cost to ensure that this DRAM chip is under the standard latency low over here. But I think there is a viable model for business also to actually have two different standard latencies and market them at different potential costs to the end user. And I think that's the smart way of doing things. But again, why is this not done? I would tell you, don't ask me, don't ask the DRAM manufacturers, but I have a guess as to why this is not done. The reason is business as usual is too good, meaning they're already making good enough money selling all of these chips, and people are buying all of these chips. Why should they change anything, right? The reason is in the end mindset, in my opinion, and that's why I've been hopefully educating you with this mindset issues. So you should be very well aware of this. I think if there was some possibility of innovation in the market, such that someone came and said, oh, I'm going to do this without being bound by the standards, then a lot of innovation will break loose. And I hope that that'll happen in the near future, as opposed to the far future. And I think emerging memory technologies could be a way to actually enable this sort of innovation, such that they can compete with DRAM and they can try to kick out DRAM from the system, let's say. They can cause that disruptive force for innovation. And maybe, I mean, I don't know how this is possible, but enabling some other company that has an innovation mindset that's not deeply rooted into this business as usual mindset can actually also disrupt the market. So it remains to be seen, but there needs to be some disruption in the market to actually enable what I just said, even though what I said is completely reasonable, right? Okay. Well, I find it reasonable, but sometimes these days, you don't know what's reasonable and what's not, depending on when some people talk. Okay, okay. Now let's go into science a little bit. Ignore business for now. So basically, as I said, conservative timing margins cause this long main memory latency, and there are multiple reasons for it. One is, well, DRAM timing parameters are set to cover the worst case. Worst case in terms of temperatures, which was not depicted in the previous picture. Basically, DRAM chips are supposed to operate reliably at 85 degrees, sometimes 95 degrees. Some DRAM is actually designed to, not designed, I should say, at least rated to operate at even higher degrees. But regardless of whatever the worst case temperatures, pick your worst case temperature that you're supposed to operate at. At that temperature, your cells are much leaky. As a result, cells are slower by nature because you leaked a lot of charge. Whereas in common case, you don't really operate at 85 degrees Celsius in general. It's actually much lower. We will see that in a little bit. But the reason you pick this is to enable a wide range of operating conditions. Right? And also worst case devices, as we've discussed, DRAM cell with the smallest charge across any acceptable device to tolerate process variation and acceptable yield. And this leads to large timing margins for the common case. So now let's take a deeper dive into understanding and exploiting variation in DRAM latency. So as I said, DRAM stores data as charged. I'm not going to go through the details of it. You activate, which brings the data into the sense amplifier. This consists of sensing, and then you restore the data back into the cells as part of the activation, as we've discussed, and then you precharge the array. So sensing, restoration, and precharge are three fundamental operations in DRAM. Now let's take a look at a simulation or a real-life example of charge. What happens to charge over time when you activate a cell? So initially the cell is charged. We're going to look at a charged cell, and the sense amplifier is precharged, as you can see, VDD over 2. So initially our charge levels look like this, and you can see the margin over here, and then data 1 and data 0 over here. Now we activate the cell. Cell shares charge with the sense amplifier kicks in, and it starts amplifying the charge at this point. So sensing ends here, and sense amplifier says, oh, I've seen enough perturbation in the bit line that I think the cell is being connected and the cell is positive, so I'm going to start amplifying the charge. So the sense amplifier starts amplifying using the amplifying circuits, and then restores the charge in the cell. And in theory, at this point, you're done. You can access the data really, really well. But in practice, we add some margin. Okay, there's some question. Let me actually take a look at that quickly. Okay. Could you explain how DRAM testing works? What do manufacturers do to test their DRAM? What is their confidence? Oh, wow. This is a longer discussion than what I intend. Maybe we can take it to Piazza, but essentially, different DRAM manufacturers have a different take on it, but they really have very expensive machines, which they connect their DRAMs to. As far as I know, they don't have a lot of FPGA infrastructures like what we have. I think they should, but they have very expensive machines, and they try to ensure that their DRAM reliability is high when they exercise the DRAM chip at the worst case conditions. So as far as I know, they do worst case testing, meaning whatever the worst case is, 95 degrees Celsius, whatever operation parameters are, the worst case voltage that the system is rated to operate at. So they pick all of these worst case parameters and they plug it into this tester. And then they basically test many, many chips. I don't know how many. They don't tell, because all of these things are actually confidential according to them. Because according to them, if they yield any information about this, you can figure out the yields, etc. But this is the high level picture. If you want to go into lower level details, we'll need to look at machines and how they do the testing. But I think this hopefully gives you a high level idea. But again, as I said, they do mostly worst case testing. For example, they do testing with 64 millisecond refresh intervals, and they try to figure out whether the chips fail or not fail, etc. I think in the worst case, it's not 64 milliseconds, some other milliseconds, 32 milliseconds, maybe 16 milliseconds today. But that's the process, basically. Okay, hopefully that answers your question, at least at a high level. But if you want to go into low levels, first of all, we need to go into those machines that do the testing. And the second is actually, there's not enough information that they provide, because a lot of DRAM manufacturers consider the secrets, which is really interesting, actually. A lot of things that you want to be known about DRAM manufacturers don't want to tell you, because they consider it as part of their business secrets, trade secrets. And if they tell you, they're extremely worried that you will go and replicate their things, which I think is a bit of paranoia, which may be good or bad. I believe a lot of it is bad today. At some point, it may have been justified when they were innovating, but clearly they're not innovating today. But they're doing it more today because they're not innovating. And if you're not innovating a lot, then you're bound to actually stick to your process, and you don't want to give it to anyone else, right? That's another interesting thing, actually. There's actually a book written about it. Maybe I'll mention it later. Okay, but why does DRAM need the extra timing margin? As we discussed, there are two reasons: process variation and temperature dependence. And we're going to cover both of them very quickly. First of all, DRAM cells are not equal, and this leads to extra timing margin for a cell that can store a large amount of charge. Temperature, let's take a look at that basically. Ideally, you would like things to look like this, but process manufacturing variation is not perfect. And not everything is the same size. As a result, not everything has the same charge. As a result, not everything has the same latency. So here I talk about size, but latency is affected not just by size, but a lot of other things, as we will see in a little bit. In the real life, you have a lot of heterogeneity. Some cells are small, some cells are large. As a result, they have different latencies. And as a result, they have large variation in cell size, large variation in charge, large variation in excess latency, as you can see over here. Again, I use size as an abstraction of things that would relate to latency, but it's not just about size. It's also about the resistance of the access transistor, for example, which is not really related to size always. It's just also about circuit defects that lead to higher latencies. Okay, so let's take a look at this process variation a little bit. Actually, I'll explain what I mentioned in the previous. This is what a DRAM cell looks like. As I said, the capacitor is dug into 70 to 100x deeper in the third dimension. And this is what the two-dimensional part looks like. So you have the contact, you have the access transistor, and you have the bit line over here. And then you have the bit line connected to something else over here, another capacitor. So you can keep extrapolating it over here. But okay, what did I do over here? Okay, access happens this way, clearly. So cell capacitance affects latency, contact resistance, access latency, and transistor performance also access latency. So these three things are important. And abstracting all of these things as a small cell is bad at all of these things. As a result, it has small cell capacitance, high contact resistance, and slow access transistor. As a result, it's slow, basically, high access latency. That's what I mean by a small cell. It doesn't necessarily mean the cell's small. Okay? Okay, so that's why you have this huge process variation. Temperature dependence is the other thing, and I've already mentioned this, leads to low extra timing margin for cells that operate at low temperature. And let's take a look at it. So at room temperature, things are not leaky. At hot temperature, things are very leaky. As a result, cells store more charge at high temperature and large charge at low temperature, and you have large variation in access latency. This is slower, this is faster, and at hot temperatures, you have also a lot more variation across the cells as well, because not all cells get affected equally by increasing the temperature. So the problem is today's DRAM timing parameters are dictated by the worst case, which is the smallest cell with the smallest charge in all DRAM products, operating at the highest temperature. And this leads to a large timing margin for the common case. So what is the idea over here? If you know all of this, the idea is simple, I think. Let's optimize the DRAM timing for the common case as opposed to dictating it for the worst case. Let's optimize it for the current temperature and the current DRAM module. Why would this reduce latency? Clearly, a DRAM cell can now store much more charge in the common case. Common case, low temperature and strong cell than in the worst case. And more charge in a DRAM cell leads to faster sensing, faster charge restoration, and faster precharging. All of the DRAM operations become faster. As a result, you get faster access, read, write, refresh also. All of those accesses become faster. So let's take a look at it. Basically, for sensing, you can sense the cells with extra charge faster. It leads to lower sensing latency. For restoration, you don't need to fully restore cells with extra charge. This is called partial restoration. This leads to lower restoration latency. And you don't need to fully precharge bit lines for cells with extra charge. This leads to lower precharge latency. So these are actually all important ideas that are introduced by this paper. And then later, a lot of papers actually took on the idea and did different changes to it to make it even better. So we characterize the variations using our infrastructure, as you've seen over here many times. And you can actually work on the infrastructure if you're interested. But let's take a look at the faster sensing first. So you have more charge, you have strong charge flow. As a result, you have faster sensing. And when we looked at it with 115 DIMMs, which is close to 1,000 chips, whenever you're operating at 55 degrees Celsius, you can reduce the timing of this timing parameter, sensing parameter, by 17%. And you get no errors. And we operated this for 3 months or so, and then you get no errors, basically. That sounds good, right? So that's one example. Reducing restoration time, as you can see, you have less leakage and extra charge at low temperature. As a result, you don't need to fully restore the cells whenever the amplifier is restoring the cells. And you can see that you can gain a lot of benefit over here. You can reduce the read restoration and write restoration by 37% and 54%. These are averaged across 115 DIMMs. It's almost 1,000 DRAM chips, basically. So these are actually very promising numbers, as you can see over here. And this is a distribution. Not all chips are equal, as we discussed. Some chips are 80%, some chips are 20%, but this is average across all of those chips. Again, restoration time reduction is possible for a typical DIMM at lower temperature because it contains more charge. And finally, I don't show the third observation, but you can guess what that is. It's the precharge. Okay, so the key idea is to optimize DRAM timing parameters online. This has two components. The DRAM manufacturer provides multiple sets of reliable timing parameters at different temperatures for each DIMM. DIMM is a DRAM module. And the system monitors DRAM temperature and uses the appropriate timing parameters. So monitoring the DRAM temperature today is easy. You can do that actually. All of the DRAM chips have support for it. The question is, who finds the reliable DRAM timing parameters? Now, if you want this to be part of the DRAM standard, so the manufacturer needs to do it, but the DRAM module manufacturer could also do it, or the end user can do it. As I said, we are the end user in a sense. We did this using our own infrastructure, and we believe these are reliable because we added also timing margins on top of what we found. Even then, we found significant reductions in latency. But again, if you're a gamer, a lot of gamers have replicated our studies. I mean, to be frank, gamers were already doing things like this, but maybe they were doing it less methodically. The work that we've described actually enabled different approaches to the gamers so that they can do it even more methodically and more aggressively than they thought they could be doing it. So even as an end user can do it. But of course, it depends on in the end who wants to do it. I think as an end user, you can do it also. But one key thing is important. Your memory controller needs to support the reduced latency parameters. If your memory controller doesn't support it, forget it. You're not going to be able to do it. Then you need to design a new memory controller, right? So the fact, if DRAM manufacturer or module manufacturers do it or system manufacturers do it, then it's much better because they can design the memory controller also. I think that's why open source hardware could be very useful because open source hardware can enable a lot of innovation in the memory controllers as well. Okay, so DRAM temperature, let's talk about DRAM temperature a little bit. DRAM standard is optimized for 85 degrees, but we actually measure temperatures and we don't see a lot of high temperature operation. And previous works also observed that DRAM temperature is usually low. And previous works actually try to maintain low DRAM temperature to minimize thermal overheads. You can read some of these papers. But I think this is interesting because it's important to think about, okay, where are temperatures going? I think in a very tightly packed system, like in an SoC, if you have 3D stacked, maybe temperatures are higher. In a server cluster, where in a desktop, temperatures may be lower. But the key is adapting to the temperature, right? Regardless of whatever your temperature is, let's adapt to it, the latency parameters. So, but in the common case, I think DRAM operates in low temperatures. So this is the latency reduction summary for 115 DIMMs. Whenever you do a read or write at 55 degrees Celsius, as opposed to worst case 85 degrees Celsius, you can reduce the read latency by more than 30% and write latency by more than 55%. That sounds good, right? So you can read the details in the paper. And we evaluated this on a real system. In this real system, basically, we were able to change some of the latencies, not all of the latencies in the BIOS. And the AMD systems are very good at that, actually. They're BIOS programmable. Unfortunately, they're not dynamically programmable, but BIOS programmable. You can see that you can change their RAS and row precharge times, and maybe more. So we actually examined real workloads, and we figured out which chips can operate at which latencies, and we plugged in our chips to the system. And then we wanted to understand what would the performance benefit of the proposal is. And we saw significant performance improvements. It's a single core workloads. They're not very memory intensive. And even then, some of the random access workloads see almost 20% performance improvements. Real system. You don't change anything else in the system. And in the intensive workloads, you get significant performance improvement, as you can see. When you go to multi-core, you get even more performance improvements because you have a lot more higher latencies because of contention. And you can see that copy workload actually improves performance by 20%. Even the streaming workloads actually improve significant performance over here. And the random access workloads still improve performance. So overall, in a multi-core system, you get 14% performance improvement on memory-intensive workloads. Clearly, memory non-intensive workloads are not interesting. They fit in the caches. They don't exercise your main memory. They're not so interesting. They exist, but they're not the common case, in my opinion. Okay, so you can see that this idea improves performance for both single core and multi-core workloads, and they're more effective when latency is a bigger problem. This also reduces row activation time, and as a result, it also reduces energy, as we discuss in the paper. So latency goes hand in hand with energy sometimes. Okay, so let's talk about the advantages and disadvantages of this. So this is a very simple mechanism to reduce latency. Even the end users can do it. It leads to significant system performance and energy benefits, and the benefits are higher at low temperature, which may be good. It's low cost and low complexity. Now, the disadvantage is somebody needs to determine the reliable operating latencies for different temperatures and different DIMMs, which means that somebody needs to incur the higher testing cost. So DRAM manufacturers can do it. I'm not sure if they're willing to do it because DRAM testing takes a lot of time. But again, I think they can be smart about how to innovate while also making money at the same time. But I think the testing may not be that difficult for low temperatures also, actually. High temperature testing is very difficult, no question about that. But low temperature testing is not that difficult. So I think the testing cost, yes, it will be higher, but I don't think it's going to be double, for example. Okay, so if you want to look at this, you can take a look at this paper. I'm going to talk about more works. I'm going to keep you for some time, and I think I'll announce that we're going to cancel tomorrow's lecture so that you can actually work on your labs and homeworks. I've taken your feedback, and I'm going to relax the schedule a little bit so that you can work on the labs and homeworks. But I'm going to take, I guess, maybe until 15 past so that we can finish latency, of which we have relatively small time left, actually. We may be able to finish in less than 15 minutes also. But feel free to ask the questions because I'm happy to answer. Okay, so this shows that there's a lot of latency variation across chips as well as across temperatures, right? And you can adapt to that. And I think that's a great idea. My student Dong Kyok, this was part of his PhD thesis. His PhD thesis was actually on introducing heterogeneity in DRAM to reduce latency. And he introduced heterogeneity in different ways. If you remember TL, tiered latency DRAM, it introduces heterogeneity in the Subarray level to reduce latency. Adaptive latency DRAM introduces heterogeneity in a very different way, but again, to reduce latency. So this is actually a very strong PhD thesis because it really has a very clear thesis statement saying by introducing heterogeneity into DRAM or into memory, we can reduce the latency significantly. And the thesis proves how much reduction in latency you can get clearly. Okay, but I think as I mentioned, this is already being applied in the field by users, not necessarily in the standards, because standards are, as I mentioned, very against innovation. But users who don't care about standards can say, okay, I want latency, reduced latency, so I'm going to do this. The unfortunate part, I think, is if they don't have a memory controller that they can change the latencies with. And I think this having a memory controller that's reconfigurable, that's programmable by the user would be really, really nice going into the future. That way, you don't need to be bound by any standard in the world. Okay, so let's talk about some different types of latency variation. So ALDRAM exploits latency variation across time and across different chips, time meaning different temperatures. The question is there also latency variation within a chip? And that was one of the next questions that we wanted to ask across different parts of a chip. And the answer is yes, basically. So we did the study across 240 chips and across many, many rounds of testing using our FPGA-based infrastructure. And we reduced the activation latency you can see over here. There are no activation errors over here, but you can see that this is the variation across the chips, basically. So if you reduce the activation latency to 7.5 nanoseconds, some chips fail a lot. Some chips really don't fail over here that much. And there's something in between. So you can actually have approximate DRAM, right? If you know the failure rate. If you go to 5 nanoseconds, now you're pushing it. Basically, all chips fail. And some of them fail at very high bit failure rates. And if you go to 2.5 nanoseconds, you're pushing it really, really badly. So you get a lot of failures over here. So 10 to the 0 means every bit fails, right? This is 100% failure rate. So you clearly have different characteristics across different DIMMs. So this is one other way of putting the different characteristics. But you can see that there's a lot of margin over here. Okay, I already said all of this. Basically, there's significant variation in activation latency. Now let's take a look at the variation in activation latency within a chip. So this is with cache lines and rows. I believe this is within a bank. You have 16,000 rows, and you have 128 cache lines over here. And you can see what happens when we reduce the latency to 7.5 nanoseconds from the standard specified 13.1. And this is the probability of cache line having more than 1 bit, at least 1 bit error. So you can see that it's mostly white. So most of the cache blocks don't have failures. Very interesting, right? Even though the chip fails overall, meaning at least one cache block has failure, overwhelming majority of the cache blocks don't have failures. So only certain columns have failure. So activation errors are concentrated on only certain columns. So this means that if you can somehow identify which parts of a chip you can access with low latency without errors, just do it. And all of the other parts accessed with high latency. That's the idea over here. Essentially, DRAM timing errors, slow DRAM cells are concentrated on certain regions. And the idea of flexible latency DRAM is it's a software transparent design that reduces latency. You divide memory into regions of different latencies, and memory controller uses lower latency for regions without slow cells and higher latency for other regions. And clearly you can expand the area to 3 different regions, 4 different regions, 5 different regions. It increases your complexity and testing complexity, etc. But it gives you higher granularity. But I think 2 different regions is good enough, as I will show you in this picture. So let's take a look at the 2 different timing parameters. This is activation and this is precharge. And let's take a look at the fraction of cells that fail, or the fraction of cells that require a particular latency parameter value. Clearly, baseline DDR3, there's no choice. You have to access everything with 13 nanosecond latencies. Now, let's take a look at 3 real modules, DRAM modules. I'm going to animate. So basically, in this DRAM module, D3, 99% of the cells can be accessed with 7.5 nanoseconds, and the remaining 1% can be accessed with 10 nanoseconds without any single bit error. And none of them need to be accessed with 13 nanoseconds at room temperature in this case. This is another DIMM. Now it has a different profile clearly. 12% of the cells can be accessed with 7.5 nanoseconds. Remaining 88% can be accessed with 10 nanoseconds. None of them need to be accessed with 13 nanoseconds. So you can see these DIMMs are different quality, let's say, but clearly all of them exhibit lower latencies. And if you know this profile somehow, you can communicate to the memory controller, and the memory controller accesses cells at the latencies that they can be accessed reliably at, as opposed to at the worst case latencies. And the upper bound is clearly something called a low latency DRAM, where everything can be accessed at 7.5 nanoseconds. So clearly this will get very close to the upper bound performance. This will also get reasonably close because remember, this one requires 13 nanosecond accesses, and this one requires at highest 10 nanosecond accesses. Okay, now we simulated 40 workloads. You can read the paper for more detail. The paper is referenced at the bottom over here. And you can see the performance improvements that we get if we exploit this within chip variation. Basically, it's significant. Now your performance is dependent on which chips you have clearly, but you get more than 13%. And the upper bound is almost 20% when we get very close to upper bound if the DIMM looks closer to upper bound, as you can see over here. Okay, so this is very promising, I think. You can, by exploiting spatial latency variation in DRAM, you can get significant performance improvements. Again, this as an advantage and disadvantage, this reduces latency even more significantly on top of what we've discussed. It exploits significant within-chip latency variation. In fact, it's the first work that exploits this within-chip latency variation. But of course, you need to determine reliable operation latency for different parts of a chip. So their testing costs increased even more. I think this is even more complex. And also, you need to have a more complicated controller to store which parts of a chip can be accessed with which latencies. Now, this was true for ALDRAM, but not for different parts of a chip. This goes to the next step, and the complication of the control is even higher over here. And today's controllers don't support it. As a result, no gamer would go to this length because they cannot take advantage of it. You need hardware changes to be able to do this. Okay, so if you're interested, this is the paper that introduces a lot of interesting characterization data and also proposes what I just discussed, fly DRAM. So if you want to put it all together, I'm going to refer you to the solar DRAM paper. It basically makes the experiments even more rigorous, and it also introduces a bunch of ideas. For example, it introduced the idea that write latency can be reduced by almost 80% with some tricks in DRAM, but I'm not going to talk about these. And this is a lot of interesting ideas. I would recommend you take a look at them. And I think this is one of the state of the arts in terms of reducing the DRAM access latency by adapting to the variations that we have. Let me ask one more question and answer it. And that question is, why is there spatial latency variation within a chip? So there are multiple reasons for it, but let me give you the one intuitive reason. And we're going to look at a subarray again. And the subarray looks like this. You have word line drivers and sense amplifiers. And the cells that are closer to the sense amplifiers are naturally faster, and that are far away from the sense amplifiers are naturally slower, because you have long interconnect distance, clearly. And the cells that are closer to the word line drivers are faster, and that are farther from the word line drivers are much slower. So you can see within the subarray, you have some part that's naturally slow and some part that's naturally fast, inherently. So this part is inherently fast because of the physical distance from the peripheral structures. And this part is inherently slow because of the physical distance from peripheral structures. Now, clearly, systematic variation in cell access times is that's caused by the physical organization of DRAM. And this is really the design-induced systematic variation. And we can take advantage of it. And I'm going to briefly talk about how to take advantage of it. And the idea is called DIVA, online profiling, design-induced variation aware online profiling. So if we can somehow know what are the inherently slow cells based on the systematic variation, based on the layout of the cells in DRAM, we can only test them. That's the idea. This reduces your testing cost significantly. We can only test them to identify the cost at the minimum latency at which we can operate them reliably. This sounds good, right? We profile only those cells that are inherently slow to determine the minimum latency. Now, this way, we can dynamically profile also to figure this out. We can do many types of profiling clearly, because your profiling cost is very low right now. So the worry of DRAM manufacturers goes away for the most part. But of course, life is not as beautiful as I just discussed, right? This online profiling is good, but it doesn't work for cells that are slow for some other reason. So these cells are slow systematically because of the design-induced variation, but these cells are slow non-systematically because of process variation, as we've discussed earlier. And process variation is usually non-systematic. If it's systematic, you can usually eliminate it. If you have systematic process variation, that means you can fix it by fixing your process. Usually, the cutting edge, good processes are left with non-systematic or random process variation. As a result, these cells are found randomly in the subarray. Okay, so now we have two different error types. Meaning, whenever we reduce latency, we may get errors. Inherently slow region gets errors. They're localized errors, and you can find out about them by systematically testing just these regions and profiling and figuring out what's the lowest latency they can operate at. You can imagine that this is a simple profiling mechanism. Basically, you keep reducing the latencies until you get bit errors, and then you build some confidence. Of course, you do testing many, many times, and then you say, okay, this is the latency where I don't find errors. I don't get errors anymore. Whereas these slow cells, due to process variation, are random errors, and these are not possible to find systematically because they're by definition random. So how do you actually fix them? Well, as we've discussed in earlier lectures, when we talk about Rowhammer and reliability, we said that these random errors are best tolerated with error correcting codes because you cannot protect them in some other way. If you want to reduce the latencies, you'll get errors. And how do you correct the errors? Well, put some error correction codes. And that's the idea in this work. You do online profiling to reduce the latencies to find the minimum latency over here. And if you get errors on these other parts, you correct them with error correcting codes. This way you can reliably reduce the latency. And because you do online profiling, you can adapt to aging issues. So one of the issues with the other works that I've described earlier is over time DRAM ages and maybe your latencies increase, and you need to somehow know about this. And if you keep doing profiling periodically online, you can figure this out. Whereas if you don't do it, if you keep your latency static, then you cannot. So this work is the state of the art because it does this online profiling, plus it combines with error correcting codes. It basically shows that you can reduce the read latencies and write latencies significantly at both low temperatures and high temperatures because we're taking advantage of the systematic variation plus error correcting codes. So this is adaptive latency DRAM, sorry. You can see adaptive latency DRAM on the newer chips that we've tested, and DEVO profiling provides even higher latency reductions. And there's some other idea in the paper that provides slightly more latency reductions that I'm not going to bother you with. But the write latency is also reduced significantly. Okay, so basically you can reduce latency more aggressively by using ECC plus online profiling. Okay, let me talk about the advantage and disadvantage of this. So a huge advantage, that's why there's a plus here. This work now automatically finds the lowest reliable operating latency at system runtime. So your production time testing cost is lower. You just need to tell or find out by reverse engineering which parts of a DRAM subarray for different subarrays are actually the slowest parts. And this can be communicated. Again, if DRAM manufacturers communicate it, that would be nice clearly. It reduces latency more than prior methods with ECC, so that's also a big advantage. And it reduces latency at high temperatures as well. So you get actually best of all worlds by paying additional costs by having in DRAM ECC, for example. Now, the disadvantage is requiring knowledge of inherently slow regions, but you can find out this by reverse engineering, like what we did in this work. But I think a nicer way is really better communication between DRAM and the memory controller, as we've been discussing. And the other disadvantage is clearly requiring error correcting codes. But I think that's a necessary evil, if you will, if you really want to get benefits of latency. I think error correcting codes are very useful for correcting random errors that you get because you want to improve performance. Okay, and this imposes overhead during runtime profiling. So similarly to runtime profiling approaches like we saw with refresh rates, you still have similar issues, but hopefully it's lower. Okay, so I'd recommend that you take a look at this paper if you have interest. It says a lot of data, and the data is all open sourced. And feel free to ask questions on Piazza, etc. So I'm not going to cover a lot of the works that I'm going to flash, but there's a lot more to discuss. Like understanding the voltage, latency, reliability relationship is really important, and this work does that. Basic idea is you can reduce the voltage aggressively, and there's some voltage margin in DRAM chips where you reduce the voltage and you don't get errors. That's good. That way you can actually improve your energy. But after some point, you start getting errors, but you can compensate for those errors by increasing your latencies. So this is another interesting trade-off. Basically, you can reduce the voltage errors. You can eliminate the reduced voltage errors by increasing your latencies of access. Why? Because reduced voltage errors happen because you haven't given enough time to the circuit so that the circuit can stabilize to a reliable value. If you give it enough time with latency, you can actually enable the circuit to stabilize. Now, let me correct myself. Not all of the reduced voltage errors happen because of this. Sometimes if you reduce the voltage, the circuit breaks because there's not enough power to do the operations. And that is also the case if you reduce the voltage too much. But there's some voltage interval where you can actually reduce the voltage such that you can play tricks between the voltage latency trade-off. And overall, this work proposed an energy efficiency improvement mechanism by taking advantage of this trade-off. Okay, there's more work to reduce that reduces memory latency to support security primitives. I'm not going to go through this in detail. I'm going to point you to some lectures, I think, potentially, or maybe we'll have some guest lectures from my students who've done these works like Jeremy and Lois. But you can generate true random numbers in DRAM, and you can evaluate physically unclonable functions when you reduce the latency. So when you reduce the latencies, so I'm going to skip to the true random numbers. When you reduce the DRAM latencies, there are some cells that don't fail always, but they fail at a 50% rate, essentially truly randomly. You need to find out which cells they are, and you find out how much you need to reduce the DRAM latencies for it. But you can use these cells as true random number generator cells because these cells are randomly failing. And as a result, they can be true random number generators. And this work shows that you can actually have true random number generators that operate at very low latency and high throughput in DRAM by doing this. And then you can reduce refresh latency by exploiting similar principles. Again, I'm not going to cover these. You can also reduce memory latency by exploiting memory access patterns. I'm not going to cover these. You can take a look at that. And we also mentioned parallelizing refreshes with accesses by taking advantage of memory access patterns as well. If you're interested in DRAM power consumption, I would take a look at this work that using our experimental infrastructure proposed a DRAM power model. There are a lot of interesting observations here on DRAM power and energy and how to model it. But I'm not going to talk about it. Basically, if you actually look at the DRAM data sheets, they tell you that operation X consumes power Y, but this is grossly overestimate. It's good to actually measure and find out the real power numbers. And that's essentially what this work is. And it provides a new power model for DRAM. And this was done collaboratively with NVIDIA, as you can see over here. Okay, let me summarize. We're almost done. Basically, I think there's a huge challenge and opportunity for future as motivated by many applications. And as I also mentioned with Satya's keynote, which I will again recommend that you watch. We want fundamentally low latency computing architectures. And I think tackling long main memory latency comes from tackling two things: the design of the memory itself and design of the fixed latency mindset, or fixing the fixed latency mindset, let me put it that way, or one size fits all approach to latency specification. And we've covered both over here. So hopefully my takeaways are clear. The first takeaway is we can reduce memory latency with a change of mindset. I think a lot of the memory latency is there because of the mindset and its limiting of innovations, as I've given you many examples of. And the second is, I think it's also clear that main memory needs intelligent controls to reduce latency. I mean, I didn't make it explicit in every case, but tiered latency DRAM requires an intelligent memory controller. CLR DRAM, CROV, all of these ideas that we've discussed, adaptive latency DRAM, DIVA profiling, DIVA DRAM, all of them require slightly intelligent memory controllers to determine what can be accessed with low latency, what can be cached, what should be cached, et cetera, et cetera. And that is needed, I think, going forward. And I think we're actually exploiting all of these principles when we discuss low latency architectures. Clearly, by nature, we're data-centric. Things are becoming more intelligent. We want better cross-layer communication, better interface between the DRAM chips as well as the memory controllers, better than worst-case design. That's what we're really doing. We're introducing a lot of heterogeneity, and we're trying to be flexible and adaptable to the dynamic conditions of the system. And most importantly, we're exploiting the principle of open minds, I believe. So with that, we've actually covered examples of all of these four key directions at this point. And I reached the end of this lecture. I've already overstayed the time. If there's a burning question, we can take it. But I think maybe the more prudent thing to do is really to leave the questions for Piazza or maybe the next lecture. As I said, tomorrow there's no lecture. So take the time to work on your whatever you need to work on. It doesn't need to be this class, clearly. But feel free to discuss more on Piazza, because there's clearly a lot more that I didn't cover in low latency memory that's interesting. And this is an area where you can actually do direct contributions to the literature as well. Okay, I don't see any questions. While I was talking, nobody typed. So I'm going to stop sharing, and we're going to adjourn. I guess have a good Friday and have a good weekend. We will see you next week.